Let me talk about use cases. Um, a lot of the students won't know who Gartner is. I imagine many of the adults on the call do. So Gartner is a very big analyst firm, and they put out what they call the hype cycle for multiple different technologies and disciplines every year. It's interesting because, it goes through some innovation that shows huge promise. People get super excited. That's called the peak of the inflated expectations. Everybody thinks it will cure everything. And then they find out actually it's not as great as we thought. And that's called the trough of disillusionment. And then the slope of enlightenment, where, yeah, actually, maybe it is useful for a few things. And then eventually it will go into production at scale and people will use it. So one of the really interesting things about this is from last year, is the highlighted things in the green box. If you asked me about them, I would say they are way on the right already. These things are all in production at massive scale, making really big impacts on the world. So this is moving incredibly fast. And if I take a look at real use cases, I'm going to go through this list. These are real things that are really in production at huge scale and making a difference in everyday lives. So the first is, and it's the thing that paid for all of this in the first place, is ad placement, search, recommenders, news feeds. Really important. Every time you use Google, every time you interact with some of the online properties, you are using this. Market hedge funds and trading. There's a reason why a lot of hedge funds have been extremely profitable over the last few years, and it's because they're actually using AI to do their trading. Fraud, intrusion, detection, intrusion detection, and security. Every time you use a credit card, it goes through AIs. All the data centers, most of the data centers in the world are protected by AI, looking for anomalies. Image processing, things like live image processing, avatars, image correction, animation, all in production today. Generative images and videos, this is where the term Gen AI comes from. I have to believe most of you have played with Stable Diffusion already. All of this stuff is very widely in use. Co-pilots. I'm sure anybody here who uses GitHub is familiar with co-pilots. Anybody who uses Microsoft products is familiar. These are becoming really normal, helpful tools. Transcription, software synthesis, and debug, these things are being done today. With natural language processing, there's multilingual translation, there's genomics analysis and prediction, things like customer service, chat things and interactive chatting. There's generative summaries of documents as well as meta research. So there have actually been some incredible scientific breakthroughs where meta analysis by an AI has gone through thousands of published papers and collated all of the data and extracted the different meanings. And there have been some serious breakthroughs because of that. Failure prediction is an everyday thing in data centers, in industrial settings like machinery tracking, and in aerospace. So, for example, jet engines on aircraft have an AI running and monitoring the jet engines for any sign of anomalies that could predict a failure. Image and video content detection and labeling, closed captioning. Every time you watch Netflix and you see the closed captioning on the bottom, especially if it's translated, that's an AI. It's done it. It's watched the video and done the translation and the closed captioning. Medical diagnosis, pharmacological research, drug discovery, genomics, those are all at the forefront of AI use. And many doctors I talk to are so excited about the new capabilities that AI brings to them in the ability to diagnose and plan for their patients. Robotics, the autonomy of machines, logistics, aerospace, and androids. Look, autonomous robots are incredibly important in warehousing now. They're used across the board. Amazon is built on that. Logistics. Amazon even they use AIs to predict placement of inventory, even so much as to place inventory in a van so that if you do the same day ordering, they've already predicted that somebody in your neighborhood is going to order that item and it's sitting on the van ready to be delivered. Manufacturing inspection, including semiconductors, has raised the quality of products being deployed, coming out of factories. And 5G and beamforming, this is one of my favorites because it's so unlikely. If you aren't that familiar with 5G cellular and how it works, it tries to reuse frequency bands in opposite directions so that there's no interference, and then it can reuse the frequencies and give you very high data rate for every customer. The way it does that is it uses antennalets and it creates beamforming signals so that it can exactly track your device even when you're moving at 60 miles an hour down the highway. There is no explicit algorithm that can do that to do the beamforming and tracking on enough endpoints for a cellular station to work. But an AI can do it, and an AI is used. So 5G every day. Mechanical generative engineering and design automation. There are a vast fleet of automotive parts now in production, very high volume, that are AI designed. They're stronger, they're lighter, and they're less expensive to make. Self-driving cars, generative scenarios for training, UI interfaces are all based on AI. Silicon design automation, this is really coming on very strong. Design synthesis, design rule checks, and cell library creation. These things are now AI-based. Cadence recently, at their keynote a few weeks ago, they talked about one design they did with Marvell, where they used an AI as a post-process, and they got a 6% improvement in power dissipation on the devices. May not sound like much, but when you take all the billions of chips produced every year and you reduce the power by 6%, it has a profound impact. And then HPC is really evolving rapidly, where AIs can be used to explore solution spaces and identify viable research points in a overall space. And then you can drill down with traditional HPC algorithms. There's algorithmic replacement. AIs turn out to be very, very good at taking heuristic data and building models for those. And then equivariance is a really interesting area to me personally, because I'm starting to see it go back and forth. It started with physics and natural phenomena, migrated to AI and has had a lot of development there. And then it's migrating back to physics. I think we'll see the pendulum go several times. And I want to talk a little bit about a few styles as well. For example, large language models, you can think of that as GPT, they deal with complex temporal sequences. And, it was originally envisaged just as parsing language. But it turns out many things are sequential sequences. And that's where we get copilots, chatbots, genomics analysis and prediction, drug prediction, intrusion detection, because sequences of events you can recognize security threats that way. Multilingual translation, document summary, and meaning. Meaning is incredibly important and unexpected, but it turns out AIs are very good at that. Meta-study research, software debug, programming, and synthesis, chip design synthesis, design rule checkers, design libraries, anomaly detection and failure prediction, self-driving. Tesla has been doing some amazing work on using LLMs for driving. If you rethink driving as a sequence of events that predict the next sequence of events, then you can start dealing with self-driving cars that way. So, and then of course, all the new use cases from ChatGPT. Embedding recommenders are kind of interesting. They're very big. These have paid for a lot of the development of AI, but primarily things like search, translation, ad placement, anomaly detection, news feeds, routing directions on, if you use Google Maps or something for directions, it's probably using an embedding recommender. And then last, HPC, I already touched on this, being able to do precise estimates very quickly, working in non-rectilinear frameworks that are very difficult in traditional HPC. Physics prediction, turns out AIs are very good at that, except maybe for computational fluid dynamics. And then things like chemical interaction and binding. So we're at the point now where instead of exploring all the materials out there and trying to figure out what they're good for, you can say, I need a material that has these characteristics. And an AI can predict that, synthetic materials are probably going to match those needs. It's a full stack problem. So I stole this marketing slide, so apologies for that, but it's actually a good slide to talk over. If I look at the bottom here, it's the hardware, right? It's the hardware layer, and in this case, NVIDIA GPUs. You can use the same software stack on data center GPUs, edge GPUs, things that are located in small data centers near where people use them, or in a like a factory setting, things like that. You can use it in embedded devices, robotics, different devices like that. And then the public cloud, which frankly is really it's data center products, but it's been abstracted, so you don't need to worry about the hardware per se. Above that is the accelerated infrastructure, and that is based on the software for GPUs and networks. Those are incredibly optimized. And then above that is the development software. And in that case, there are multiple other things involved. There's pre-processing and post-processing. So things like vector database, analytics, transformation of input data, and then training at scale in a large cluster format, and then optimizing, taking the trained network and optimizing it, pruning it, tuning it for inference, and then deploying at scale. But there's another layer on top of that too, which even if you're using PyTorch or frameworks like that, there's another layer which typically wants to be tuned for a specific domain area. And those are things like medical imaging, speech, robotics, maybe autonomous vehicles. So the entire stack is necessary in order to build and deploy effectively. And this is a breathtakingly large amount of software, and it must be tuned because the amount of resources required are just immense. So scale and power is an unexpected side effect of AI. Again, I want a piece of history here. There's a big tip-off. I did this slide in 2020. But I took the trajectory that I was seeing of cluster sizes, represented by GPU count on the left, it's the green line, and cluster power, that's the blue line. And I graphed it and I said, well, something needs to change. And the reason I said that is that red line is 40 megawatts. There weren't any data centers larger than that. That was the limit of a data center. My assumption was we were radically going to have to change how we did things, or train models more slowly, or limit the size of the models. Turns out I was wrong, because if you look at data centers being built today, they are right along that line. The radical change here is that it is not okay to be limited by anything but your imagination on what we can do with AIs. Changing computer architecture. This is what brought me into AI in the first place. Was the realization, again, these are marketing slides and they're kind of cartoony, but they're good to talk to. On the right is GPUs. They have a high bandwidth interconnect between them, an x86 processor, and DRAM. It turns out the real problem here was the x86 and the DRAM were an incredible bottleneck. The PCIe bandwidth is simply too little for feeding these high-powered GPUs. The DRAM is insufficient for maintaining bandwidth to the GPUs. So what we did is we changed the architecture. In this case, Grace is an ARM-based CPU. We did that because we didn't have an x86 license. So this is a 72-core ARM data center CPU, and we used LPDDR5 instead of DDR because you can get an incredible amount of bandwidth through a massive number of channels and have a huge number of outstanding transactions. The bandwidth is about 10x what you could get out of an x86 processor, and the GPUs are no longer starved. And in fact, so much bandwidth that the GPUs can actually drive the bandwidth of the LPDDR and use it as a massive second tier of memory. Slow, yes, for the GPUs, but it changes what you can do. And then just because they're kind of cool, a couple of pictures of the latest generation. On the left is a Blackwell GPU. This was on my desk the other day. I just took the picture. There are very few of these available yet. It's not in full production yet. But you can see there are two massive die in the middle that are butted against each other. Each of those die is the biggest die you can make in the most advanced process there is. So it takes two of them to act as a single Blackwell GPU. And then you see 8 stacks with little skinny bars, bars that are spacers. But the 8 stacks are HBM3E memory. Each one is 8 device stack of memory. It's about 192 gigabytes and somewhere around 3 terabytes per second of bandwidth. On the right is GB200, which you see 2 Blackwells at the top. The Grace, the CPU is in the middle with LPDDR, and at the top are NVLink connections. And that's about 1.8 terabytes per second of communication bandwidth per GPU. And what people are building from that is a massive data center, 72 GPUs in a single rack, and then scaled out rows up to this particular cluster is 32,000 GPUs. You may have seen in news some people have been talking about building 100,000 GPU clusters from these. But that's not all that's changing. It's changing the data center architecture too. And if I kind of roll back, the general, if I start with the silicon level and work my way up, it requires general capability. You can't over-optimize because neural networks are changing every 6 months. They change what is needed and the balance of those things. If you over-optimize, it will not be appropriate in the future. We try to offload 100% of the work to the accelerators. The CPUs are too slow. They become an expensive I/O processor and memory controller. The cadence on platforms is increasing to yearly. This is because the rapid evolution of AI is requiring this. We're required to try to keep up with that 10x year-on-year increase in capability. We're focused on smaller precision floating point, multiply accumulates, sparsity. Interestingly, the most efficient work you do is the work you never do. So it turns out a lot of weights are zero. 0 times anything is 0. So if you can take advantage of that, you can actually increase throughput and reduce power at the same time. Memory bandwidth capacity is increasing, and we're learning how to shard memory across large clusters of capacity. And communication is interesting. The communication is a critical enabler of AI training. In even AI inference. I'll talk about that a bit later. But that GPU I showed you has 1.8 terabytes per second of communication bandwidth. That's about 140 times a normal data center 100 gigabit Ethernet. It's 17 times the highest available network bandwidth. And if you have a computer at home with a 1 gigabit Ethernet, it's about 14,400 times your 1 gig Ethernet bandwidth, just to give you something to compare to. And then the silicon keeps getting larger and more capable. We're now at multiple full reticle die in one package. If I look at training, the clusters are moving. They moved from 4K to 8K to 16K, 32K now. Public discussions of 100K. Next year, you can expect 200K GPU clusters. I am having serious discussions today with hyperscales, guys like Meta, Google, Microsoft, Amazon. What is it going to take to build a 1 million GPU cluster? And just to, kind of make it clear what the investment there is, a 32K GPU cluster is around $1 billion. So this is not something people talk about lightly. We focus on a static cluster configuration so that we can control the communication very rigorously and get zero collisions and ensure that we can extract 100% of the potential bandwidth between these devices to communicate. So we are orchestrating the communication in the entire cluster at once. And then on the inference side, it's really interesting. We were using CPUs for inference, and then it moved to a GPU for inference, and now it's really GPU systems and small clusters. So, for example, on ChatGPT, if you're using that, every time you ask GPT a question, you're activating about $500,000 worth of hardware. And then also, most client devices at this point either have or will have shortly our accelerators inside. And on the building architecture, we're now doing crazy things like going multi-story so that we can use the 3D shape of the building to shorten all of the interconnect and the optical cables. And that improves cost, it improves reliability, and it improves latency and therefore throughput. So we're actually changing how we build data centers. They're all having facility liquid cooling now. They're actually physically strengthening the floors because the mass of these platforms, the density is so high that a lot of floors were never designed for this kind of weight. And then in order to distribute the power, we're having to move to higher voltages as well. And interestingly, power is one of the biggest roadblocks to increasing. And we're seeing a move to private power off grid. On grid, the coherent swings of power consumption in the data center on a massive cluster are so much that it actually reflects back into the grid. That's not acceptable. You don't want your lights at home getting too bright or getting too dim with each, every 20 milliseconds as the AIs are cycling through their stages. So there's a lot of focus on safe nuclear for private power plants, and everybody is focused on multi-gigawatt power. And then other crazy impacts that we've seen. The build out of this infrastructure is so fast that copper futures have actually gone up. The price of copper has gone up. And in the energy sector, we're seeing growth. It is about 3% of the power in the country. It's moving to about 10% in 2030. The AI network cadence is mind-boggling. The state of the art changes about every 6 months. And so we need to look ahead. We need to predict what will happen. If we take state of the art today, the new hardware will be obsolete by the time it lands. Security and privacy is critical. If you think about it, where does somebody want to use their most valuable data? It's to train an AI. And what is one of their most valuable assets? It's the result of that trained AI. So AI platforms become an incredible security target. And there's a lot of work on confidential computing to completely obscure anything that's going on there, and a lot of government pressure as well. On the roof lines, we're constantly pushing the petaflops, the terabytes, the communication bandwidth, and the memory capacity. And as a cluster gets larger, it becomes more brittle, and we have uptime issues, and that slows down training. So, for example, a 32,000 GPU cluster today has about 4 interruptions per day. We're working across the entire stack to improve the resiliency and the uptime. And at the silicon level, we're pushing the limits of what's possible to make in a die. We're pushing the transistor speeds and packaging technology. And we're actually having to make sure that the whole ecosystem has the capacity. We've had shortages over the last few years because different ecosystem partners were unable to produce any more of whatever it was they produce. Delivering power to the rack is a critical problem. Thermal density is an incredible challenge. And then dynamic synchronous power is also a problem I discussed. And then finally, the impact broadly, sort of summarizing. For chips and semiconductors, we already have AI design and test integrated, and there will be more tasks done by AIs. Failure and service prediction, we're increasing the AI telemetry and monitoring in the data center and using that to predict failures. For power delivery, we're increasing voltages, we're providing more gigawatts and moving to private power generation. For the dense thermal solutions, we've switched into liquid cooling from air cooling and created really dense data centers. Memory, we're investigating new memory types. I keep holding out hope for new memory, but it doesn't look good. Die size limits, we're trying to figure out novel packaging and way to make multi-die devices. The AI accelerators are going everywhere now. And one of the interesting things that's going to affect embedded devices is they need to be updatable in the field because AIs are changing every 6 months. And embedded devices will become more powerful and capable as well. And then data and model security has created confidential computing as a technology. So just to kind of summarize and leave you with some things to think about, this is a rapid AI evolution, and it is not slowing. It's actually probably increasing in cadence and adaptation. We need adaptable platforms to accommodate that. We're pushing the envelope on compute, memory, communication, and security. The capability needs are growing at least 10x year on year. It's been 10 years of history. It is not slowing down. This is pretty mind-boggling. The scale of the workload and the type of workload and the density is changing architectures and infrastructures across the world. AI is now driving all engineering disciplines to advance rapidly. We are seeing very rapid changes in any engineering and science area caused by AI. AI is now the biggest spend in data centers worldwide. It will become a big part everywhere else. I mean, eventually it's going to be in your wash machine. AI will become part of everything we design and do. So if you are looking at any sort of career in engineering or science, AI will be an important tool in everything you do. And by spending the time now and learning this technology, you'll be really well placed for any endeavor you choose in the future. So with that, I'm done.
Thank you so much, Rob. That was amazing. And I learned a whole bunch of things I didn't know. One of which was that I did not realize Amazon preloaded trucks. In hindsight, that sounds like such an intelligent thing to do, but it never occurred to me that they would actually do that, because sometimes I do wonder how they managed to get this much stuff delivered same day. So yeah.
Well, fascinatingly, they also do things like one of their inputs is weather. So, for example, if there's rain coming or a heat wave or anything like that, for a heat wave, they'll start pre-positioning air conditioners, for example, portable air conditioners. So it is fascinating. That is a core capability they have.
Yeah, no, that is fascinating. I think I'll get to the questions in a moment. The second thing I think I really liked was the idea of meta research analysis because so the head of research from Meta, mentioned in a panel about 6 months ago that there were 600,000 AI research papers published in the first half of 2023. And her point was, don't even try to read them all. You're just not gonna. So you might as well get something else to read it and tell you what it all means. So let me go through some of the questions. So one question was, you already mentioned like 10x growth. What do you think will be the size and capability of AI training clusters a decade from now? I mean, it's
I
kind of it
it
boggles the
it
mind.
it I have to, well, okay. So let me say a few things. I have to believe that at some point we will have sufficiency. Um, but if I look at a biological model, it means we're going to need tens of millions of GPUs, for example, even as every generation of GPU gets more capable. I don't know if we'll get there. For years, I've expected us to asymptote on the computational needs. That has not happened. And so I am humble enough to say, I'm not sure I can predict. This could go on forever, or it might slow down in 10 years, but it's certainly not in the next 5 years. There is no slowdown at all.
And is the power coming from, are we drawing power from somewhere else, or are we simply building new dams or finding new ways to create power that didn't exist before?
We are pulling from, it depends on the region. Sometimes it's new power plants. Sometimes it's reallocation of power. Other things are getting more efficient. So, some of the consumption has gone down. But this is why all the large data centers are discussing private nuclear power plants. It's green. The new style of nuclear is safe. And so they don't really feel like they have any choice. That's probably what we'll end up with because, like, even renewable energy, solar, wind tends to be unreliable and also tends to be especially unavailable at night. So, which is when people tend to use things. So they can't rely on that.
Oh, that's really interesting. So for the students, what this tells me is that for those of you who are working on low power, and there are quite a few of you who are looking on low power solutions to existing problems, they are not limited to the edge. They're useful everywhere, even if.
Yes, absolutely.
So another question that's here is, what are the primary challenges associated with training a large model like GPT-4o at 25,000 GPUs over 3 months? How does that even work? Yeah.
It is a challenge. It's an operational challenge. I mean, a better way to think of these is as, let's say, a token factory or a factory. So things are incredibly operationalized. It is about efficiency and cost effectiveness and throughput. Um, so there will be items failing. When you get to this scale, any individual component rarely fails. It'll fail. You'll get, a fraction of a percent every year will fail. But in aggregate, across this immense number, you are getting failures, and especially soft errors, like software errors based things, um, all the time. And I said, the typical numbers we're seeing in a 32,000 GPU cluster is a failure, 4 times a day, or a crash. Maybe that's a better way to say it. Crash and a restart. So we're going back to old high performance computing habits, which are to do checkpoints and restores. And we're optimizing how fast those can happen because we will get crashes. There's no way to stop it at this point, and they're going to get more common. So we're attacking every layer of the stack. The hardware is becoming more reliable. We're working on ways to make it more resilient. Same with the communication stacks, and same with the overall data center cluster software. So it's 1,000 cuts, and we're just doing the best we can.
Makes sense. So I think next question, and we have a few minutes left, I think. The audience member says, I want to know what you think about where generative AI will go from here. What are the things you're hearing that you're allowed to talk about, not specific companies, that are cooler than what we've seen?
Um, okay, there are some very interesting things happening. A lot of them I can't talk about, but what I will tell you is the thing that has shocked me is that in every endeavor that people have tried to apply AI to, it's worked at least pretty good and sometimes spectacularly well. And I don't think there's a single endeavor, a single human endeavor that is not going to be impacted by AI. And things like LLMs are a prime target. One of the fascinating things is researchers, and I do get to talk to some of the leading researchers. I know the people doing the work at OpenAI, for example. Um, well, one of the really interesting things is as the models get more complex and larger, they do actually train easier. They can train on less data, and they can generalize better, which is sort of shocking and counterintuitive. Um, but I think we will continue to see the growth in model size, especially mixture of experts is enabling us to dramatically grow the size of a model. And I think we're going to find just amazing universality, and we'll be able to use avatars to, for almost anything. Almost anything. My imagination isn't even as good enough to give you ideas.
No, no, thank you. I think that's really, I mean, it's something I have also noticed. So maybe one of the takeaways possibly for the students is, at least one thing I noticed, is that whenever I think something and I think, oh, that can't be possible, I ask GPT, apparently it's already been done. So, and I've been trying these, every random thing I can think of. Can you use X to detect Y? Can't be, right? No, no, been done. So yes, there's a lot of that kind of stuff going around. So no, makes a lot of sense. And yeah, the mixture of experts, if anybody else has questions, follow up. It's a very powerful technique that, has been used in the latest GPT models. So I think a few other questions. So
Actually, on the mixture of experts, it is a lucky coincidence that I talked about the architectural changes where we're introduced the CPU bonded to the GPU and have the extra memory, high-speed memory. It turns out that platform is exceptionally good at running a mixture of experts because you can offload experts that are not being used at the moment into the CPU memory and page it in and out very rapidly.
wow.
So I think we're going to see a real explosion there.
Oh, that's delightful. That's good to know. Yeah. So a few additional questions. I mean, and these are questions that a lot of people ask me. The one question is, how far are we from AGI?
Ooh.
Everybody's got an opinion. I think we're interested in yours.
I my opinion is I think we're a very long way from that. I think it's easy to get lulled into thinking we're close to it because a lot of the models today give that give that feel. They feel like they know what's going on, but when you peel back the covers, they can go terribly wrong. And actually, that's another cautionary thing is that as useful as these things are, you always do need to kind of double check because they really, really do hallucinate things, and that is an ongoing problem with AIs. Is they overfit and they will hallucinate things that aren't actually real.
Absolutely. And then I think one question, maybe one final question regarding climate change. How do you feel about what is the general kind of thought on, I mean, these massive, massive data centers, so big now that they're building their own nuclear power plants? Yes, AI is being used to improve climate, but it's also just chugging along and consuming energy like there's no tomorrow. So I'm curious, what is the broader sense of thought among these big companies about this? Or is it more that they're like, okay, well, it is what it is?
There's a certain ambivalence. I have an ambivalence. I mean, all of the large hyperscales are working towards carbon neutrality. But we're also, I think we're able to do things that have never been possible before. So that's an advancement of human endeavors that is unprecedented. So on the positive side is that we can do things we could never do, but there's an incredible amount of energy being used, and that I think is exactly why there's a movement to safe nuclear. Some of the liquid salt, different kind of nuclear power plants, because we can actually power these things and get those benefits without any particular environmental or economic cost. So I think that's the hope is that we don't have to have that trade-off. We don't have to worry about it.
So thank you so much, Rob. This was an amazing keynote. Everybody, as I know there were many requests for the recording, so the recordings of the entire symposium will be sent to everyone who registered. But thank you so much, and really, lovely to connect with you again, and I learned a ton. So
Yeah,
really appreciate it.
fantastic.
Thank you,
My,
Rob.
my pleasure.
So next up is our second keynote speaker. I am going to just bring her just for a moment before. Wait, what am I doing? Yes. Hold on. So I'm going to share her bio for just a second. Hi, Surbi. So Surbi Kaul, she is the Vice President of Customer Experience at Nile. For those of you who don't know Nile, I'm not sure if they're quite stealthy, but they are a very, very well-funded new AI company. Surbi has a great deal of experience in various kinds of AI products. She has built things at Google, YouTube, Netflix, and she's been in many companies. And she has a lot of experience with the product side of, building these really large and, AI products that tons and tons of people have used around the world. So let's welcome Surbi and feel free to share, Surbi. Thank you very much for being here.
Thank you, Nisha, for inviting me. Such a pleasure to be here. And I'm assuming, just to gauge the audience, that it's primarily high schoolers, middle school students, or do we have other audience as well?
So it will be primarily high school, middle school students, their parents, some
Okay,
educators, and other, interested parties. Yeah.
awesome. Awesome. So please let me know when you can see my slides, and I will go into presentation mode.
Yes. And also there are teachers here as well. So.
Okay, perfect, perfect. So
Thank you, Monica. Yes.
okay, great, great, Nisha. Thank you. So I would love for the session to be interactive. If anybody wants to ask a question, please raise your hands, and I will call on you. If I don't see them, Nisha, if I can request you to support me there. And if I get too much in a flow, maybe you can pause me so we can address questions as we go. I have a lot of content, so based on where interest is, I can go deeper, or where, there's less interest, we can skim through the things. But I will talk more about my own journey with AI and how I have become familiar and well-versed and engaged with various AI products that I have built over time, and how I myself have carved a career that is around AI. And of course, when I started my journey, like many of us, AI was not front and center in most of the conversations. So it's an interesting time, and we're all up leveling and changing our skills and our thinking every day as newer and newer tech innovations are coming up. So as Nisha mentioned, I work for Nile. I head their operations and customer experience, and this is a slightly different role. If I can share a little bit about my journey with all of you. I grew up in India, and I did my primary schooling as well as my undergrad in India. I got a degree in aerospace engineering at IIT Kanpur, which is one of the engineering schools in India. And then I came to the US to pursue a master's in computer science. So basically, I came to Texas all the way from India and did my master's there, post which I was hired on campus. I'm sure many of you go through that route or are looking forward to going to that route where you get interviewed on your campus and then you start your first job. So from Texas, I came to California to do my first job at HP. It used to be the Google of those times, a very well-known company, very well-respected, well-sought. So here I was a little junior engineer in a big, massive company. And from there, I went on to Cisco Systems, a networking company. And that's where I sort of serendipity happened, where I got into the networking space. And then from there, I have been fortunate enough to go to many B2B, what we call business to business and business to consumer. So companies like Facebook, which now Meta, or Google or Netflix, they're called B2C, business to consumer, where you build and create products for consumers, so users like you and me, versus companies that build B2B products. So companies like Cisco Systems, where they're building networking equipment or any infrastructure equipment, it's business to business, where they would sell to other businesses. So I was fortunate enough to work at both B2C as well as B2B companies. And then I spent about 10 years at Google, which is where I would say that I got extreme exposure to machine learning and AI capabilities, even before it was a very mainstream word and recognized. And then post Google, I went again into the B2B space of working at Juniper Networks, which is again a hardware company, infrastructure, and now at Nile. And then along the way, though I started as a networking engineer, I did move into product management, and I've stayed in product management for almost 15 years. And if there's interest, I can talk a little bit about that. A lot of times students are very interested to know how they can become product managers or what product management is all about. And I teach at UCLA, I teach product management. So that is something I'm very passionate about, because you don't directly get a degree in product management. So you have to figure out how you would, become a product management manager if that was something you were interested in. And at Juniper, I moved to do customer experience, which is a different discipline, I would say, than product management, but a very important discipline. And that's becoming very important these days in enterprise companies that want to build easy to use products, which is a very much a mindset of consumer companies. And now at Nile and outside of work, I also do a lot of engagement with my alumni association, which is where I know Amit and Nisha from, which is why I'm here today. And I also sit on the board and advisory roles of a few startups. I mentor and coach startups as well. So that's a little bit of my history and my journey and my meandered through various roles and various companies to get to where I'm at today. And along the way, I would say machine learning and AI ML happened in my life. And I would say my first exposure was about 10, 11 years ago when I was at YouTube. And for you, some of you middle school and high school kids, what you may not know, that YouTube used to be a very static platform where you would go in and you would search for some content, you would observe and view that content, and then it would pause, and then you would have to go and search for another content. So what we today, commonly refer to as recommendation engine, which is it'll tell you what could be the next interesting video for you, or Netflix would show you what is the next set of movies you might want to watch or content you may enjoy. It's recommending, it's making a suggestion to you. All of these are machine learning based capabilities that were not there early on. But as you start understanding your customer base, you start understanding what are the likes and dislikes of people, then you can really surface what is a recommendation for them. And at the time that I was in YouTube, we even started this concept of autoplay, which is the idea that if you started playing a specific genre of music, maybe I can serve you the next music without you having to go and query. So you're optimizing and making the journey of your customers very efficient. So you're not waiting for the next query, you just say, and it has two advantages. One is you're building efficiency and improvement in how your customer is able to get value out of your product. The second is also your ability to to keep them on the platform, to keep them hooked onto your platform so you can serve more advertisements to them, which is how a platform like YouTube or Meta monetizes themselves, is by keeping consumers or users as long as possible on the platform. what we commonly call as daily active and monthly active DAUs and MAUs. You will hear this term if you are in the industry, or if you do internships, you will see in these companies, these are metrics that are very commonly talked about. So this was the beginning of my machine learning journey. And then from there, I also was fortunate enough to, test drive a few of these autonomous cars as Google acquired Waymo. And, they were always interested in finding test users. So I had the option and ability to test drive. And it was a very exciting time because there was, a lot of new things, a lot of nuances that were coming up in how we would make the self-driving more efficient. And now it's, of course, it's a very common aspect that you see in whether it's in Tesla or, Waymo cars or others. Many self-driving cars are around there today. And in San Francisco, you can even book a car Waymo that'll take you around. So we have come a long ways, but this was my journey. And then face recognition, Nest cameras, Google Home devices, these were things that that I got exposed to also during my Google time to understand how machine learning is able to create a lot of positive impact in the community and for the users. And I'll talk a little more about that in my presentation. So this was how I started getting exposed to machine learning. But the first thing before we go deeper, I want to give you a very high level definition, and this would be for people and listeners here who have not been as exposed to it. For those who are already in this space or very familiar with it, might already know it, but I'll just do a very high level overview that when we think of artificial intelligence, it's actually anything and everything that where you're trying a machine to make a machine act like you are making a machine act like a human. So it's taking the human intelligence and trying to see if it can be artificially generated. That was the naming of artificial intelligence. And then out of that came a subset, a smaller field of machine learning, where it says that instead of trying to program specifically what the machine or the program in this case tries to achieve, you give it a lot of data and you help it learn on its own. So you're not doing explicit programming, but you're giving it a lot of, for example, a lot of images of cats and dogs or other animals, and see if it can classify itself what these various tools are, or what these various subsets are. And then when you give it a question, then it's able to answer your question, whether the picture that you're giving it is a cat or a dog or a horse or things like that. So that is where you get into machine learning. Recommendation engines are another good example. And then an even smaller subset of that is deep learning, where you are creating a very human brain-like like topology of saying, I'll give you a set of inputs and you have to create a set of outputs. But the way you do that is you create neural networks in between. And these are millions and billions of connections, exactly like we have in our brain, that's start correlating data to be able to create a human-like output. And natural language processing and speech recognition, all of these are aspects of deep learning. And from these three, this was a commonly known pattern before November 2022. And if somebody can, just shout out if you recall what happened in November 2022. And I heard that question for the previous keynote speaker as well, is generative AI. Generative AI was made or became familiar, we became familiar with generative AI in November 2022 with the launch of ChatGPT. And I hope, all of you are familiar with ChatGPT. But what happened in that time frame is that up until now, we were giving very clear instructions to the machines on, what is it that we want the machine to do, or how to create the rules and structures that we were feeding the machine learning or the deep learning solution. And then based on that structured approach, it would give you the answer or give you the information, but it's very much within that structure, and it's very much based on a rule-based thinking and system. Here with Gen AI, we created the ability to really generate content, generate an answer, generate some data. And I'll give you some information that almost 7-8 years ago, when I was at Google, we were thinking about how do we make Google search, for example, more useful for the consumer, where the thinking is that when you search something, instead of giving you a list of websites, which is what the old way of giving information was, you give a list of best websites. So Google crawls all the internet and says, if you ask me a question about some topic, let me give you the top X websites based on my ranking that would be useful for the answer that you're seeking. However, that is not the most efficient way because the user still has to go through those 10 websites and figure out what the right information is. So the thinking here is, can I take all of that data set that I have from these first 10 or 20 or 30 websites, and can I really suss out and give the user the right information so you're very quickly getting that information at your fingertips rather than having to go through the 10 sites. So that is what generative AI did. And now you can see that everybody, every big company has got onto the bandwagon of saying that, can I use generative AI to make the journey of my customers more efficient? Even Google now, if you go search on Google, you will get that, that generated answer based on everything that the Google crawler has seen. So that's the concept of generative AI. And if there are any questions, we can address those. But if I take you back a little bit in history, this is not something new. We have been talking about machine learning for a long time. In fact, in the 40s is when Alan Turing came up with the question of, can machines think? And he gave a seminal paper. He talked about a test where if you are behind a screen engaging with a computer, can you really tell if the response is coming from a human or for the machine, what today we call chatbots, right? And the idea is that if the person who's doing the test is not able to detect whether it's a computer or a human responder on the other side of the screen, then you have passed the Turing test. Then you have truly built a machine that is able to emulate a human-like conversation. That is the idea of a Turing test. And we have been talking and thinking about this since the late 40s, starting with the 47 seminal lecture of Alan Turing in London. So the thing is that now is when we think that we are getting very close to answering this question, even though we have been looking at it for 70, 80 years. So my question to all of you is to think about, are machines really getting smarter? If you think about it, and I'll give you some examples. In the 50s, Arthur Samuel, who's also considered a very sort of a visionary in the field of computer science, he actually programmed the computer to play the first game. The first game that we ever did was tic-tac-toe, where now the set of the rules are very limited and the number of moves are very limited in tic-tac-toe. However, the point is that you can really train a machine to be able to think what is the next move and a few moves ahead to start acting like a human, right? And then from there, we went into chess, which is a more complex game. And in 1997, actually, IBM has created this machine called Deep Blue, which could play chess. And it was able to defeat the chess grandmaster at that time, that was Garry Kasparov. And Deep Blue defeated Garry Kasparov, and that was considered a big, big feat in the computer's ability or a machine's ability to think and engage like a human. And then in 2016, again, while I was still at Google, we had this extremely, how should I say, extremely debated and the, very high profile event where AlphaGo, which had been trained for years to play the game of Go, played against the then champion Lee Sedol. And we had, I think it was best of 3. And I'll tell you that the days that we had this in Google, nobody was working. The productivity was shot because guess what? All of us were glued watching this game to see if truly we can get to the level of beating a human in this game because the complexity of this game is much higher than the previous two. This is a game of true strategy. This is a game where you can have billions of outcomes. Every move can actually result in billions. So not only is the computer computing all of those, the computer thinking of all those strategic moves, but also has to think about how to circumvent the possibility of losing its pieces and losing its ground. So if you don't know of this game, I would say read up on it. It's an extremely interesting game of 19 by 19 grid, and it takes a lot of strategic thinking to decide how you would win this game. And then AlphaGo was able to win this game, really setting machines into taking them to the next level. So my question that I was asking earlier is why now, right? Why do we feel that we are at a place now when we have been talking about it for 70, 80 years? And I'll give you some answers. So as you will see with time, our complexity and our ability to do more and more things through machines is increasing, right? To the point that we are now at a place where a machine is able to generate a work of art, to generate a movie script, to generate any collateral that a marketing team or a product team would use or need. So we have come a long ways from that initial game of tic-tac-toe. But what has changed? One of the big things of our reason for being able to democratize artificial intelligence is the ability of resources, right? The compute and storage and infrastructure needed to run such big programs is there today, where its resources are much more cheaper, much more easily available. So if you think of 20, 30 years ago, we did not have the ability to stand up this many CPUs and GPUs. For example, I'm sharing with you what was used in AlphaGo, more than 1,000 CPUs and more than 100 GPUs. That is a very expensive set of resources. And it was also not available to one company, one organization. Along with that, there is ability to innovate very fast that has happened. Because you can now, over the last 15 years, everybody has become very familiar and comfortable with cloud computing, where if you wanted to test something out, you can quickly go and spin up an instance in any of the big, cloud providers like Google, Azure, or AWS, and then be able to iterate and test and play with your ideas to see if you can come up with new creative solutions. So ability to innovate is extremely high today compared to a few decades ago. And then the next point is that there's a lot of open source data and a lot of open source platforms that are available, like TensorFlow is available through Google. ChatGPT has come up with OpenAI that you can use and engage with. You have Llama from Facebook. You have so many other products that are open source and available to users to engage with and come up with new models, right? So you do not have to build everything from scratch. You can start from one of those models as you are thinking of innovating and coming up with a new solution. And then the biggest thing I would say that has helped our ability to be leading the generative AI as well as all machine learning capabilities that we are building is the availability of large data sets. As I will talk about in a little bit, is to train any model, you need data. Without data, our ability to really train models and to be able to build such large models that our previous speaker was talking about, it's not possible. So data is there today. And we have, because of this infrastructure democratization, we have the ability to clean and manipulate a lot of this data to produce good, healthy models. I wanted to share a few generative AI use cases that, as we had been talking about, where we have moved in this AI ML space, we are able to do a lot of creative things based on generative AI. And these are some of the examples that we are using in companies, in organizations today. So first and foremost is ability to create realistic images and realistic video. that can help me create my marketing data, that can help me create my, web blogs, that can help me engage with my customers in a very meaningful way, that is completely putting us in a different level of efficiency, right, with our image generation. Next is summarizing tests, summarizing text, and I hope you all are not using it for your assignments and homeworks, but you could test and check your assignment to make sure you're doing a good job. In fact, in my UCLA MBA class, a lot of students last year asked me, is it okay if we use generative AI for doing some of our assignments? And I said that, generative AI can help you improve your writing, but the original thought process will still have to come from you. That human touch will still have to be there. And that's how we are using summarization or even text generation in our organizations. Then writing assistance, if I have to create documentation for any product I'm creating, generative AI really helps me do that efficiently and quickly. So if you look at all of these examples I'm giving you, these are examples where human efficiency is improving tremendously through the use of generative AI. Now, it has its downsides as well, and we'll talk about that. But our ability to really improve our efficiency of all our employee base, as well as, students, as well as teachers, is all there. And then last, my favorite is the language translator. We use it a lot in how we today create web pages, and we can quickly translate those to any new country where I want to launch my product in. I can quickly create a website in that language without putting in as much effort of hiring a translator, hiring a web developer, etc. And those of you who are Star Trek fans, you remember there used to be a universal translator that the crew would take out to be able to talk to an alien. And here we can see a future where you take out a translator to talk to not an alien or non-human, but other humans in other countries. As you travel, as you want to learn a new language, as you want to engage and learn about cultures from other countries, you can do that, all of that, much more easily through the use of generative AI or through tools and apps on your phone that can help you engage more meaningfully. So I just wanted to give you a few examples. And my favorite example of Gen AI is a chatbot, because this is exactly where you start, sort of clearing the Turing test that we talked about earlier, that when you are engaged with, for example, a website, and you go to the help section of the website, the first set of communication that you're having as you're explaining your problem or asking your question is with a chatbot. But chatbots of today are very limited. After a while of engaging with you, if you ask it a complex question, or if you have a more atypical problem, which is not within the structure that the chatbot has been trained on, it'll typically send you to a human. So we still have limitations on those chatbots today, but the goal is that that chatbot should become so intelligent and so capable in the future that you are actually able to resolve your complete issue by just having a conversation with a chatbot. And the chatbot should be so aware of context and aware of the issues and aware of, what the circumstance and context is where you're coming from, that it's able to resolve your issue exactly like a human would. And that's when we would truly pass the Turing test. Okay,
So
any
since
questions so far?
yeah, there are a number of questions on the chat. Perhaps I can read them out to you.
Yeah,
Uh,
sure.
so let's see. So one question is actually, how did you get into product management, and what should students study to get into this field?
Yeah, that's a great question, and I'll tell you that the answer to that is multifold. There is not one field that you can go into and say, from here I can become a product manager. But the good answer is that you can become a product manager from any field. Whether if you're studying econ, or if you're studying mathematics, or you're studying data science, all of those fields, the starting point would be in different places, but you can come into product management from any of those areas. Because if I can just spend a few minutes explaining what product management is about really taking an idea and pain point of a customer and building something that solves that pain point, or taking an idea and turning it into a product. It's truly where you are working with all aspects of product development, whether it's engineering or design or test or launch, marketing, all of those areas you work with. You're at the center of a product, center of a, how should I say, you're like the CEO of your product, right? Where you own all aspects of your product. So if you think about it, any of these peripheral teams that you're working with, whether it's marketing or engineering or design, you could be a member of any of those teams and make your way into product management. And because it's a known fact that product management is not a discipline that you can get a degree in, it's very common to encourage people from other disciplines to come into product management. And when I started my journey in tech, it was very common for people with MBAs and people with marketing degrees to go into product management, because their primary goal was to work with customers, to be outward facing, and to ensure that their product is getting visibility outside, doing webinars, going meeting customers. So very sales oriented and outward looking job. Over the last 20 years, with the advent of companies like Google and Meta, where the thinking is that product managers need to be very technical, I saw a lot of product managers coming from the engineering side, from the design side, from the QA side. So today we are in a place where no matter what degree you have, if you have the desire and interest in becoming a product manager, you can make your way towards product management. And any product management organization is always looking to bring people in from various facets of that, of the disciplines, various disciplines, into product management, because a product manager has to be able to think about all those aspects and wear many, many different hats. So if you are, for example, a math major or a data scientist or a marketing major, any of those can help you get into product management. I would say that you are not limited by your degree. Does
Thank
that
you.
answer your question?
Yeah, it looks that way.
Okay.
So the next question, if you don't mind taking another one.
Yeah, sure.
So what would be a major that will help a student to understand AI and
Mhm.
learn things that they need to be a skilled worker when they graduate? So I
Yeah,
think
that's
yeah.
sorry, go ahead.
I was just going to say, I think it's about kind of like the thriving in the AI world. Right?
Yeah. And I'll tell you, this is a question I get asked not just by students, but also by my current teams, right? By the marketing teams that I work with, the sales teams that I work with. How do we need to pivot ourselves, our skills, to become very AI centric? And what I'll give you two answers. One is the answer that I give for, people who are already in the workforce and doing their jobs. I want them to start thinking about how AI, or specifically Gen AI right now, can improve the productivity of your role, your world. So the existing workforce, I tell them, don't think of AI is here to take over what I'm doing. Absolutely not. Think of it, AI is here to help you be more efficient. A document that was going to take me 3 hours to write, maybe I can just create an outline, and Gen AI or Llama or a Chat GPT can help me write it or improve upon it within an hour. So you have made yourself, 50%, 70% more efficient to be able to up-level yourself to do more strategic things. So the day-to-day things that were taking up a lot of your time, that can be outsourced, or that can be punted over to generative AI kind of tools. Now, for students, I would say that the landscape of machine learning is changing. It's changing pretty quickly and pretty rapidly. So what I would say is that make sure you still have your fundamentals very strong, right? And when you think of fundamentals of machine learning and any AI model, it's your mathematics fundamentals if you're going down the math path, your econ fundamentals, finance fundamentals if you're going down the business path. All of those fundamentals, make sure they're very strong, because the tooling at the top, whether you're using Gen AI or any machine learning capabilities, those are applications but your fundamentals, if they're strong, you will be able to adopt to the changing landscape of the higher level products and tools. I also want to inform and share with you people that there is a lot of free training and education out there around machine learning. And I would urge all of you to take some classes to be well versed in the jargon of AI, to understand when somebody is talking about, machine learning or recommendation or reinforcement learning, what do they mean? So ensure that you have some basic understanding of the terminology. And then if you truly go into that science of being a data scientist or a ML engineer, so the difference between a programmer that is writing code for any product versus AI/ML would just be that you are also incorporating machine learning concepts, but you're still programming. So if you keep your fundamentals clear and solid, then you would be able to pivot very easily to building ML models versus just writing code versus building a code for a hardware or whatever else you could do. So I would say a few things for students: make sure whatever discipline you're going in, you understand the fundamentals of the discipline really well. Second thing is ensure that you understand and are familiar with the AI jargon and abbreviations and terminologies. And third thing I would say is do take some classes, on whether it's as part of your school curriculum or even outside. There are many, many platforms that give a lot of good education at a very reasonable or sometimes even free. So take advantage of those and ensure that you understand these things.
Great. So I think there are a few other questions. Maybe you can take one more and then let you kind of finish. There's
Sure,
some
sure.
questions about any thoughts on the issues generated by Gen AI, such as compromising deep fakes. So the kind of the
Yes.
darker side of generation, right?
Yeah, absolutely. I think, and I have one slide on AI ethics that I will talk about if time permits. Otherwise, I can also take it offline. You can connect with me on LinkedIn and we can discuss. There is definitely this is a concern that anybody who understands the field well will share with you, that while there are lots and lots of advantages and lots of use cases, like I was showing you previously, where we are building efficiency, we are democratizing education, we are democratizing healthcare, our ability to reach all remote areas to provide good healthcare, whether it's in villages or smaller rural areas through Gen AI is going to be phenomenally impacted in a positive way. There's also a lot of concern about things like deepfake, things like how data and consumer information out there on the net, whether it's on Instagram or Meta or any other social platform that we choose, how that can be used in a way that is very detrimental to our society. And there are those concerns. And the way that we have to start thinking about is how to protect our own data. So we have to take a little bit of responsibility ourselves to say, how can I protect my data and my identity by not sharing too much of your information on social platforms easily, restrict it to people you trust. Don't put information and data on platforms that you don't trust. I mean, Meta itself, being so well known, still had a breach. So there will be breaches. So you have to protect yourself. That is one thing. Then the other thing, I think there are many layers of responsibility. So first thing I say to the younger generation, especially because there's a lot of trust that you have grown up with on machines. People of my generation are more wary because we grew up without these machines. So when we have to engage with machines, we still have a little bit of that trust issue. How much information can I put in? Can I put my social security number in clear? Can I share my phone number, my home information? But a lot of younger generation does not have that trepidation, where they have grown up with a lot of trust in these machines. They have grown up making friends online, sharing personal information with friends online, but you don't know who's on the other side of that name or that persona, somebody claiming to be a teenager. You don't know if on the other side of that online teenager could be a pedophile, could be a criminal, could be a stalker. We don't know that. So first, responsibility is our own to ensure that we do not share too much. Second responsibility I put on the corporate America, the platforms themselves, the Googles, the Metas, the Netflix, the Insta of the world, to say that TikTok, another one, to make sure that you're protecting consumer data. Our users of today are putting a lot of private information, and it's extremely important that these companies put guardrails around protecting their privacy, not just from breaches to bad actors, but also internally how they use that data to give recommendations. For example, yes, we all like recommendations, but there has to be a boundary on how much, where that ability to understand a user gets into creepiness. You don't, for example, I'll give you an example. When I was at Google, they're very, very strict about sharing data, and Apple is even more strict, which I really like. But we anonymized all the data. But I could, based on a user A, without knowing much about them, I could really connect a lot of dots to say, this is where they're on the Google map. This is where they are most of the time. So I know this is their residence. This is the time their shopping habits. This is their travel habits. So you can really know and learn a lot about the person. So the second level of responsibility I place is with these companies who have a lot of user data and a knowledge about their habits, whether spending habits, travel habits, etc. And the third responsibility is with these, there are a lot of governing bodies that are in place, and there are more and more coming up, which is a good thing, because we need to ensure that on a higher level also, we are creating guardrails on how to protect our people, our schools, our education system, and all of that against the bad actors who, if they get hold of these capabilities and tools, can really cause a lot of harm on a large scale. So there are several layers of responsibilities that have to be put in place. And the challenge is that the technology of Gen AI and other machine learning capabilities are evolving so fast that for these governing bodies to keep up with it, to ensure that you're creating quickly the guardrails. It reminds me of that road runners, that the train is coming at full speed and you're kind of building the railroad as it comes. We are in that mode, that we have to be very quick, very agile to create guardrails so we are able to, get the benefits out of the technology without, causing too much harm to our communities and our people.
So I think we have about 3 minutes left, Surbhi. So perhaps we can just take a couple of questions. I think
Yeah.
that inputs have been very, very valuable. And so there was a question here that somebody already gave one answer to, but I'll ask again. What
Yeah.
newsletters would you recommend to the kids to stay on top of AI related information?
What news?
Or just, what kind of newsletters? Is there a newsletter they could subscribe to, something that you might recommend, maybe something you read, right?
Mm-hmm.
That helps you stay on top of what's going on.
Yeah, so I do read, I do listen to a lot of podcasts and read articles on WSJ. I would encourage, which is Wall Street Journal, I would say one thing to students, that there is a lot of data out there. There's a lot of information being generated. So you have to be careful of what you consume, right? Because not all data is good data. In fact, I have a slide on that I wanted to share with you. There's a lot of bias in our data, right? So even the news that you consume, you have to be careful of where you're getting it from. I would find people that there's a place called Medium where people, leaders write articles or share their thoughts. There are a lot of good articles there around machine learning, AI, ML. There's also, I will look up some of these things, Nisha, and share with you, and you can share with your community on what are good places to get information. I read a lot of stuff on the net, but over time I have curated a list of sources that I trust, right? And I would not want our students to just read everybody and anybody, because different, views could be detrimental rather than positive to them. So maybe I can take this action item with you, that we can come up with a list of things to distribute to the students on where what are good places where they should go to get the latest and greatest information and maybe stay away from the others.
Yeah, I
Right?
think that would be wonderful. Absolutely. So we will definitely share it with our
Mhm.
community and with everybody who has, registered for the symposium today. I think, Surbi, that also it's not just for kids. The education world is inundated by people who have declared themselves to be AI experts
Absolutely.
the last
Absolutely.
year, and to the point that it's causing like havoc and frustration as well. So
Yeah, yeah, I could not agree more with you, Nisha, that it's very dangerous how many people, and I used to hear this phrase when I was younger. It was called little knowledge is a dangerous thing. And now now I'm truly understanding what that phrase meant.
yeah,
So there is so much to know, so much to learn. And if you're getting half-baked information from people who are not experts themselves, it's not it can be detrimental to our upcoming generation. So yes, we will definitely give you clarity on what are good sources of information that you should seek.
yeah, absolutely. So for those who are on the call, we will communicate with Surbi, and her recommendations we will send out again. So I want to kind of thank the speaker. I know there was a slide there on bias. If it's okay with you, Surbi, perhaps if you're comfortable with us sharing your slides
Yeah,
with
absolutely.
audience, we
I'll
can
share my
definitely.
slides because I had a lot more data. And so a few challenges I wanted to share, just call them out. One is the bias. The other is context, where the machines don't always have the context that we humans are able to very quickly understand. Like if you look at this picture in white, we know it's a cat, but a machine may not be, despite being trained very well, may not be able to. Not saying forever, but these are challenges. Or a self-driving car, experiencing things on the street that it has never seen before, how that would react. And if I can say one last thing, I know we fear a lot with generative AI, but I do want to call out that my most beautiful experiences have been when our products inadvertently help, people in need, which was not. Sometimes you're building products to monetize them. But for example, when I was working at Google Home, we got a letter from somebody who was not able to, who had to wait, a 16-year-old kid who had to wait for his mom or parents to wake up because he could not move his bed or sit up. And when Google Home was able to help him, move his bed, turn on the lights, be able to do so many, play music, engage with anything he wanted to in his room without having to wait for a caregiver, I was so touched. So technology has a powerful impact on humanity, but we definitely need to watch out for the challenges as well.
Yes. Thank you so much, Surbi. Really appreciate it. And a
Yeah,
wonderful talk. By the way, please feel free to stay and, watch some of the students present.
absolutely. Yeah, I'll do
So
that.
we will start the student presentations. So I'm going to share my screen for just a moment.
Yes, I'll stop.
Let's see. Okay. All right. So we will now have a series of student speakers. They will each have 10 minutes to present, and I will introduce each speaker at a time. You can see that there's a very wide range of presentations. So our first speaker is Rohan Arun Kumar, and he will be speaking about FireSense, which is a technology to integrate deep learning with ESP32 microcontrollers for improving forest fire surveillance. So go ahead and take it away, Rohan. You can share the screen.
Okay, sure.
I will give you a note at the 8-minute mark. Okay?
All right. Okay. Okay, so can you see my screen?
Yes, we can see your screen.
Okay. Oh, never mind. Something went wrong. Do you mind if I just quickly reshare? Sorry about that.
Of course, feel free.
Yeah.
I think I'll probably give you an update on the 7-minute mark because so that we can have a little room for questions as well. Go ahead.
Okay. That's weird. It's not. Sorry. It's
No
not
worries.
showing it on my end.
What's the issue?
It's not showing me the screen.
Okay, can you try sharing again?
Yeah, this should be the last time.
No worries. So we are able to see it. Are you able to see
Okay,
it?
yeah, I'm able to see it now. Sorry
Perfect.
about that. Yeah.
No worries.
So just to introduce myself, my name is Rohan Arunkumar, and I am a rising sophomore at Dr. Ronald E. McNair Academic High School in Jersey City. And like Dr. Nisha said, my project's name is FireSense, integrating deep learning with ESP32 microcontrollers for enhanced forest fire surveillance. The problem that I am addressing with my research are the side effects of forest fires. Due to climate change, the frequency and intensity of forest fires have been increasing every year. This results in ecological damage along with economic troubles because fires cost a lot of money to combat once they're big. So this means that the best way to reduce that will be to detect forest fires before they peak. There are existing solutions to detect forest fires, but they detect forest fires only after they're very large. Some of these solutions are detection using satellites and routine surveillance of the forests using drones. To solve this problem, I decided to build an AI model that can detect forest fires when they're small, and finally use that model with a cost-effective device that can be deployed in forests. This will reduce the time taken to report forest fires to authorities. The overall approach followed to solve the problem starts with identifying a dataset which has enough images of forests with and without fires to build a deep learning model. In our case, we have used the FLAME dataset. Then we built a deep learning model by performing transfer learning on a few pre-trained convolutional neural network CNN-based models. Next, a cloud deployment service was used to deploy a model and make it accessible via an API. After that, we built a device using cost-effective controllers and components that can use the API and detect forest fires. This device would not only be able to detect forest fires before they become big, but also send the alerts to appropriate authorities. The base models that were used during training were MobileNet v2, ResNet 101 v2, and NASNet Mobile. These models were altered using hyperparameters such as learning rate and epochs, which affected every model's accuracy rating. On the validation dataset, MobileNet v2 achieved a maximum accuracy of 99.4%. ResNet 101 v2 achieved a maximum accuracy of 98.3%, and NASNet Mobile achieved a maximum accuracy of 98%. On the test dataset, we took the best model, and this was MobileNet v2, and once it was tested, it resulted in an accuracy of 98.1%. In order to practically use the AI model that we created, we developed a device. The device's components receive directions from a cost-effective microcontroller, ESP32. This microcontroller acts as the heart of the device. The device has a simple setup, only needing two components apart from the microcontroller, in which the microcontroller actually contains a camera on its head. The additional components are the servo motor and the battery. The servo motor is basically a motor that will just spin, and the battery, of course, supplies power to the device. The final model is then deployed on the cloud, where the device can utilize it whenever it is needed. The process that we have followed to create the deep learning model is presented on this flowchart. In summary, the dataset was downloaded, pre-processed, and stored since it contains images. Then it was split into three distinct sections: train, validation, and test. The train section is used for the model to learn, and the validation section is a preliminary accuracy check. The test section is a final accuracy check. Using the appropriate data sections, the models were trained, validated, and tested. If the preliminary accuracy was above a certain threshold, this test accuracy is then recorded and the model is converted into ONCS format for cloud deployment, so it'll be available via an API. In real-life situations, the device will run autonomously, but for demonstration purposes, a touch sensor was included to take pictures. Once the sensor detects a touch, the camera will turn 45 degrees in a direction specified by the above conditional. After this, the device will be captured and sent to the AI model, where a prediction is received through the cloud API. This resulting prediction is then sent over email. After all these steps are done, the device gets ready to repeat the same steps. To conclude, the issue of forest fires remains ever so pressing, with the rates increasing in parallel to climate change. This research proves that machine learning techniques are a powerful resource to combat this issue when paired with an appropriate device. The final model we created has high accuracy, and the device is affordable and sustainable, making this pair seamless and reliable. This solution has many real-life applications, with the most feasible being that devices can be deployed on forest trees. This works due to the lengthy camera range of an ESP32 camera, which is approximately 1,000 yards. Using this metric, the amount of devices per forest can be calculated, leading to this application being very optimal. Another possible application involves devices situated on top of drones, but this would not be optimal as shaking may impact picture quality. Such applications are endless, but limitations do apply. In the future, many steps can be taken to expand upon the general sphere of this research. The same device can be used in different ways, such as animal tracking and deforestation prevention. Additionally, a more efficient device can be developed with a longer camera range, lower expense, along with other improvements. Lastly, the current device can be tested in actual forests to get an understanding of its efficiency along with potential problems. And thank you for listening to my presentation. If you have any questions, please feel free to ask.
Thank you, Rohan. Really nice presentation. Does anyone have any questions? Let's give a minute. So it sounds like you have a number of different plans for future, right? Is there anything that you're looking to do first?
I think the first one I would try to do is get in contact with a local forest and test out the actual device to see if there's any limitations that I overshadow. So that would be my first step to take.
Wonderful. And I think there was a question also related in a similar vein. So
Oh, yeah.
thank you so much and wonderful work. Thank you, Rohan.
Okay, thank you.
So let me just share my screen again. So let's see. Sorry, if I could figure out where my scroll went here. Okay, so our next presentation will be by Krishna Agrawal. He has developed a novel multimodal deep learning approach to estimate the shelf life of agricultural produce, which you can tell is a really important problem because the world throws away a lot of food due to, wasted food due to them going bad. So welcome, Krishna.
All right, thank you. And I'm just going to be sharing my screen.
Okay, go ahead, Krishna. Yeah.
Okay, can you see my screen?
It's loading up. Yes, I can see it now.
Okay. Hi, everyone. My name is Krishna Agarwal, and I'm from Foothills High School in California. And like Dr. Nisha said, my project is a novel multimodal deep learning approach to shelf life estimation of agricultural produce. The problem of food waste is immense in our world. Each year, 1.3 billion tons of food is wasted, while 780 million people sleep hungry. The amount of food we waste yearly is enough to feed the entire hungry population 4 times over, showing a large disconnect. Nearly 50% of food is discarded in the farm-to-fork process, as seen here. Due to inadequate storage, transport conditions, weather, pests, and incorrect decay estimation. Previous research focused on classification and biosensors. Classification identifies decayed produce, which doesn't prevent waste. Biosensors predict decay based on emitted gases, but this method isn't reliable across different types of produce. My solution uses image regression AI models to accurately predict decay in organic produce, currently focusing on strawberries and tomatoes. Our device captures images, processes them in real time, and delivers actionable insights to farmers and distributors, which improves supply chain management and reduces waste. Step one of my approach is making a regression model to predict the decay in singular produce items. Firstly, I gathered my data set. The data set consisted of data on images, temperature, and humidity, as well as time until decay. Next, I split the full data set into three subsets: training, validation, and testing. Then I selected a few base models from Keras. The most promising ones were Exception and Mobile V3 Small. I customized and experimented with the neural network layers of the base models. I then proceeded to constantly experiment with different hyperparameters. The hyperparameters were epochs and learning rate. With each change, the models exhibited different error rates. While I recorded both validation and training stages of the process, both validation and training experimentation occurred with their respective subsets. If the model performed very well or had a very low mean average error, it was saved as a candidate for the final model. Finally, the saved models were evaluated using the final test dataset, which helped determine their real-life reliability. For my regression model, I created a custom dataset for my model to train on. The developed dataset contains more than 2,000 samples of tomato and strawberry decay patterns, which were captured in a multitude of environmental and positional conditions. The tomato model exhibits a 2.8-day mean error, and the strawberry model has an average error of 1.8 days. When the average lifespans of the produce and limited data are considered, these are great results. The second step of my approach was to build a detection model to isolate individual produce items and create a system that could work efficiently on large batches of produce. To create the detection model, I firstly created a data set by gathering images of batches of produce online. This data set was also divided into three subsets: training, validation, and testing. I used a YOLO V8 base model for the experimentation process. The experimentation process is also carried out through constant tuning of hyperparameters in both the training and validation phases. The mean average precision, or MAP, of each experiment was recorded. The mean average precision, or how precise the positions of the bounding boxes are, is displayed as a percentage. If the percentage of the MAP 50 was over 90%, the model would be saved. The saved models then underwent the examination given by the test dataset to help determine which model was the best. The detection dataset comprises images of batches of tomatoes and strawberries from the internet. Bounding boxes were manually placed over these images to isolate singular produce items within the batches. The final dataset included about 250 images. The results for the detection model also came out very well. The mean average precision was almost 96% after 75 experiments. The graph shows how the MAP changed over the epochs. I'll show here. I used a Raspberry Pi for, the last step of my approach was creating a hardware device that can combine the capabilities of both models in an effort to make implementation in food sectors easier and more efficient. I used a Raspberry Pi for Model B equipped with a Raspbian OS, a camera, and environmental sensors for its versatility and sufficient processing power. Combining all three steps in my approach, here's the final device for workflow. Firstly, we have the batches of agricultural produce, ideally being monitored by the camera and environmental sensors. Images of the batches will then be monitored by the detection model, which efficiently crops isolated singular produce items. The regression model then uses the images of the isolated produce, temperature, and humidity to predict when the produce will decay. Currently, the value that the system values as the most important is the lowest amount of days until decay in individual produce, so that supervisors can resolve the matter sooner if decay is near. Even if there is a long amount of time until decay, alerts will be sent through email with the amount of days until decay and a few tips on what steps to take to preserve shelf life. Here's a demo video that shows all the steps in action. Okay, so this right here is the actual hardware that I created with the Raspberry Pi. And these are the tomatoes that it's monitoring at the moment. So for demo purposes, it's like a live feed, right? Like you can see when my hand waves under it. As of now, it's just a live feed for demo purposes. And when I save it as an image, you can see the window close. Okay, so after a few minutes of processing, we see that a new image pops up. And this image shows the days until decay. And it also sends me an email. Okay. So from my research, I learned that multimodal neural networks can accurately predict decay in produce, and the shelf life of produce can be estimated accurately by combining regression and classification. The research has also led to the development of a device that contains the model's capabilities and is ready for employment. In the future, more models can be made to predict shelf life in different types of organic produce. Additionally, for existing models, more data can be gathered to reduce already minimal error. An end goal for the project is to be able to implement it in real-life scenarios. Thank you, and please ask questions if you have any.
Thank you very much. Very, very nice presentation. So there are a few questions on the Zoom message. So one question is image regression, using instead of classification with multimodal is nice. How did you make it regression? And how did you make it multimodal? What did you need to do?
So basically what I did, I'm gonna answer the second question first. So multimodal is basically like it uses two modes of data. And in this case, the two modes of data are for both images and the humidity and temperature, which are which are regarded as like numbers, right? So like a text based. But then so to make a regression, right? So for future I used the image path, and I used so what I did was I imported detection models, image detection models from Keras, and we customized the models so that we removed the top layer so that it would no longer be detection, and we added a regression layer, and then so from there it became a regression.
Okay, very nice. So I think there are a few nice comments for you as well, and then people feel like it's very cool and could help a lot of people. Very nice job, Krishna. Wonderful.
Thank you.
So next up, I think we're making excellent time. Next up, we have Anya. She will be speaking about low-cost adaptable computer vision laundry assistance for the visually impaired. So take it away, Anya.
Thank you. Okay, wait, let me just quickly share my screen.
Yeah. If you can turn on your camera as well, if you're okay with it, please do.
Yes. Just, okay. Let's see. Oh. Here we go. Okay. Okay. So my project, well, let me first introduce myself. So my name is Anya Tujil. I currently go to Cattle Middle Magnet in Shreveport, Louisiana. And my project is LALAVI, which stands for Low Cost Adaptable Computer Vision Laundry Assistance for the Visually Impaired. So I have to go a slide forward and then I'll go a slide back. But so my project started whenever I heard about one of my dear family friends, Miss Patty, who suffers from pseudoxanthoma elasticum. She is visually impaired, and whenever a 46-year-old washing machine broke down, she had to find a non-working washing machine of the same model located hundreds of miles away. She had to find a repair technician who knew how to fix it, and then she had to pay a lot more money than would kind of be worth, considering that he was 46 years old. So I looked on the market to try and find an innovation that she could use that was kind of simple and that was universal. And then after doing some more research, I found out that 15% of the world's population has some form of disability. 20 million of the U.S. population has some form of visual disability, and then more than 1 million Americans are completely legally blind. So although 7 million people have uncorrectable vision loss, only 1/7 of that actually are blind. So I wanted to create a innovation that could identify the selected cycle on a washing machine control panel, that could provide an audible guidance based on wherever the light was, I wanted to make it universal, and I wanted to make it accurate and simple for someone to be able to operate. Okay. So after doing a little bit of research online, I went to the stores to kind of figure out where I should start. So I took a survey of the Washington in the market. I went to 2 stores and I found 3 types of interfaces. So I had light-based knob-driven, which you can see here. So they're ones that you cannot tell the difference or what cycle it's on. And then I have tactile-based panels, which are here, which she could tell the difference between. And then other styles were just things that had a combination of the 2, but still wouldn't be accessible for her. So the majority are light-based. So my solution was to create a device that could detect and recognize the selected washer cycle by correlating the position of the light. So I started by using a Raspberry Pi. I have to find the slide. Okay. And then I programmed it in order to fit my home washer because that's what was near me. And then I programmed the Raspberry Pi to be able to take a picture whenever it noticed that there was that something changed. And then I put it through the 6 steps of the OpenCV program, which is the Open Computer Vision program. So it goes from original to grayscale, which that's to remove any noise or anything, then to blur to simplify it, threshold to only focus on the lit up parts, eroded to make it smaller and more kind of visual, kind of to allow it to detect the most, and then dilated, which is just to kind of blow it up to really make sure that it had the right position. And then the last one is selected, which it takes the brightest point, puts a red circle around it, and then it would put it through like the end of the flow chart, which I have a picture of later, and it correlates the location of the light by finding the text-to-speech file, which I have correlated based on the location already. So not only is it able to announce all of these cycles that are around the edge, but it's also able to announce on and off, which is boot up and just off. So I found that actually in the end that the on cycle actually took the longest, which was to be expected, as it had 14 lights that I had to recognize, while normal was the fastest because it only had to recognize 1 light. So I used a Raspberry Pi 4 with a 32 megabyte micro SD card and RPI operating system. I used a Raspberry Pi camera that had autofocus, a small portable Bluetooth speaker, and then I also had several different RPI packages, including Python, Pandas, and Google Text-to-Speech. I used Autodesk Fusion 360 to design my final arm, as you can see here. It's this part, like the white part. And then I use Google Text-to-Speech to make MP3 files for each of the different settings. And then I wrote an OpenCV program to run the whole device. So this is my final thing. So it took a picture on this little red spot right there. And then it would run it through the OpenCV program, and then whatever would, and whatever cycle it ended up being, it would go to the Bluetooth speaker, which is where it was announced from. So for my data set, I had a few different data sets. So the first one was the test data, which was set up with the RPI camera. And then I had all of the program cycles, excluding on and off. And then I had a separate one for on and off. So the way I used AI in this was by using OpenCV for image perception, which was how I figured out where the location of the light was. And I also used it for blob detection. So you can see here a more in-depth breakdown of my system. So it goes start, then I created the sound files. It captures an image, it identifies the location of lights, and then while it's doing that, it captures another image to make sure there's no difference. It converts the image to grayscale, it blurs it, it thresholds it, it erodes it, and it dilates it. And then it identifies the number of LEDs. So now if there's 0 objects, 0 lights, then it will announce that it's off. If there's 14 lights, the max number of lights, and it will announce that it's on. And then if there's more than 0, but less than 14, which is the max number, it will play one of these depending on the correlating location. So then after this, it stops and then it will continue running again once it notices that a change has occurred. So I ended up putting all of my values into a table. So for each of the 16 settings, I ran 5 rounds of testing. So I ended up doing 80 tests. And so I found that the normal program was the fastest with an average time of 0.8 seconds. And the on cycle was the slowest with an average time of 3.13 seconds. Once again, as that was because of the fact that it had to identify all 14 lights in order to produce an accurate value. So then once I had that done, I put it into, I put it into a box and whisker plot to just kind of visualize all of my results. And as you can see, on was a clear winner. And I mean, for the slowest time, and then that normal was the fastest time. So these small dots, if you don't know, I'm not sure if you guys know or not, but those are outliers. So essentially, sometimes it just took a little longer than normal, or it was a little faster than normal. So that's how I portray those. So I ended up learning how to complete a wide spectrum of tasks all at once. I learned how to assemble, configure, and program a Raspberry Pi. I learned how to design a 3D mount, and I learned about statistical analysis and visualizations. Oh, wait, is that it? No, it's fine. Okay. So some challenges that I had were how to operate the updated Raspberry Pi operating system. I had used it last year with my other science project, but there was a new updated version, so I had to figure out how to operate that, and then also how to program through OpenCV and connect to the Raspberry Pi camera and get my system working with 100% accuracy. So I have a small video. Oh.
Speed wash. Permanent press.
Yeah, that's my video. It just, so again, it just takes picture, it runs it through the OpenCV program, and then it will announce it. So my system had 100% accuracy, and it was able to announce it correct and in a timely time. So in the future, I would like to make a more compact system. I would like to minimize the system. That way it can just kind of sit on top of the washer instead of having to create a pretty big obstruction over the top. And then I would also like to create a web-based sharing so that it's universal and anyone can get on it and program it very simply and easily. And then also replace OpenCV with YOLO because it is able to constantly monitor it a lot more than OpenCV. Thank you.
Thank you very much. That's a wonderful project. I just had a couple of, I think there was a question about how long it took you to kind of do it, the thing end to end. Just curious.
Oh, like from the start of the project to the end?
Yeah, because it involved a bunch of experiments and, you know,
Yes.
data.
So I would say, I think I started this about December, and I'm pretty sure I finished about January. So I did most of it over my Christmas break. So it didn't take me very long. I just did most of it in one day. And then I did testing over 5 different days. That way I could ensure that the light was the same, that it would work in any circumstance.
Terrific, wonderful. So one idea for you, you have gathered a really nice data set. You might want to publish that for use by other, researchers. You might also want to create a kind of an infrastructure where perhaps if somebody, even a washing machine company, right? Or somebody has a washing machine, just tell them, take the same experiments you did, and that way they can contribute. So you did it on your washer at home, which most of us would, but then
Yeah.
maybe you have a friend who has a different kind of washer, who can then gather up the data and then, and you can build something for their washer. So very nice job, Anya. Thank you so much for presenting. So next up, we have, I love the variety of topics that we have today. So the next up, we have cord blood, I'm not going to pronounce this well, cord blood creatinine estimation using machine learning and genomics. Go ahead, take it away, Wishruth.
All right, so let me just. So can you see my screen?
Yes.
All right. So my name is Vishrut, and I'm a rising senior. And my project is based on utilizing clinical and genetic markers to estimate neonatal exposure to maternal smoking. So just a quick description of my project. So this project is oriented around predicting neonatal cord blood cotinine levels to indirectly assess the effects of maternal smoking. Um, so there we go. Okay, so my hypothesis was that a machine learning algorithm can measure and estimate the fetal exposure to maternal smoking by predicting cord blood cotinine levels with a mean absolute error value less than 10 using clinical and genomic expression information. So maternal smoking during pregnancy negatively affects fetal development. This can result in low birth weight, increased risk of SIDS, which is sudden infant death syndrome. Maternal smoking can also alter transcriptome of placental and fetal cells, which can also negatively affect important biological systems. So assessing fetal exposure to tobacco still remains relatively difficult because many mothers may not self-report accurately. So this ML model aims to develop a framework that combines clinical and genetic markers to predict neonatal cord blood cotinine levels. And that is a biomarker of tobacco smoke exposure. So in this manner, I hope to use this research to expand to a level where I can accurately predict the level to which a mother's exposure to smoking will affect her unborn child in the attempt to properly prepare for when one's child is born and provide an effective pre-birth analysis to support the child. So a quick software overview. So this entire project was completely Python based, and I used Google Colab, Pandas, NumPy, scikit-learn, and Matplotlib to complete this project. So going into that data set, so the data set was collected from NCBI, which is the government database for biological systems. And we first downloaded a clinical data set and a genomic data set, and then we merged the two into one consolidated set to use for training and testing the algorithm. After this, I went through a feature engineering process through which we removed like unnecessary data in columns like NaN values and other things. After this, I went through the process of converting the categorical columns into numerical columns using one-hot encoding. And then finally, the last step was to identify the top 20 upregulated genes within the data set itself.
Yeah.
So for the AI used, this was a traditional 80-20 split for training and testing, respectively, after creating the data set. And so I used the random forest, XGBoost, K-nearest neighbors, and multi-layer perceptron machine learning algorithms to test and see which algorithm provided the best RMSE metric results. And so just to clarify, this was a regression model. So the next two slides are just the experiment process. So this one is just detailing everything I mentioned before, but the basic overview is just like going through the training and testing process after the 80-20 split and creating the data set, getting the best RMSE values, and then identifying what the best algorithm was, which was XGBoost for me in terms of my results. But this table quickly just illustrates like the hyperparameters and their ranges as well as what I use to tune the algorithm for better results. So for example, random forest used number of trees and max depth, XGBoost used max depth and number of estimators. K-nearest neighbors only had number of neighbors as a hyperparameter, and multi-layer perceptron uses learning rate and number of epochs. So these are some of my results that I just graphed out using Matplotlib. And so these are just trying to show the validation RMSE for each algorithm with respect to their hyperparameters and the number of tests that were done. And so this is just a table that outlines everything that was mentioned. And so these are the best results in each category for each algorithm. And so going back on my results, I saw that the best RMSE value I got in XGBoost. And for R squared, this is a metric which goes from 0 to 1 in terms of how it's measured. And if you get a negative value, as I did from random forest and K-nearest neighbor, what this means is that the algorithm doesn't fit the project at the best level possible. So at the end of the day, I was able to say that random forest and K-nearest neighbor were not the best fits, but that XGBoost had one of the higher scores, which means that it's a better fit for this project. And overall, looking at all of the different metrics, such as the MAPE, which is the mean absolute percentage error, and the MAE, which is the mean absolute error, I saw that XGBoost overall gave me a collective result being the best and most efficient. So with XGBoost, I was able to accurately predict the tobacco exposure by estimating the cord blood cotinine levels of any given patient. And the overall scores for all the metrics utilized, again, came out to be the smallest in XGBoost. So this algorithm thereby adjusts the broad context of the problem at hand and how the potential issue of false reporting for smoking from patients or the unawareness of potential smoking issues for the patients themselves can be avoided completely with this project. So the MAE was 8, which reached our goal in our hypothesis of a score less than 10 as an error average. And altogether, this study presents a promising methodology for predicting cord blood code 9 levels in patients that indicate their tobacco exposure. With the help of advanced machine learning techniques and genomic information, I'm able to provide a tool that's efficient for healthcare professionals to use to assess tobacco exposure levels accurately. So I think some of my main learnings from this entire process were to devote like a substantial amount of time towards pre-processing for the data set because it can take a long time. And that was one of the very tricky parts of this due to multiple NaN value columns, lots of one-hot encoding work to do, and a lot of online library searching to go through. And also maintaining clean records of your work will always save you time in the long run because I had to go back, had to refer the genomic information. And so it would have helped even more if I kept even cleaner records than what I had. Yeah, and as mentioned before, one of the hardest challenges was definitely the data set itself and pre-processing because it took a long time. But another one of the challenges was using matplotlib and creating the results graphs, and also using scikit-learn because these were two libraries that I wasn't comfortable with when I first started. I didn't have much exposure, but through this project, I was able to gain some nice experience on those libraries. So I have a demo video, but it's quite long. So just to outline really quickly, this is just outlining like this is one of my spreadsheets for testing. I also just showed off like the basic training and testing collabs that I used and the basic code and how like I set the test and train values and how I split them and then how I use the regressor. But for the most part, that is all. Possible future work for me may include expanding the data set to accommodate a wider range of patients, tuning hyperparameters even more to get a much more nuanced and practical result. Also, real-time prediction of these medical issues will consist of many other features. So there can definitely be more features that can be added to this program to make it more applicable in the actual medical field. And as for all algorithm scores for the metrics can always be improved with more training and testing. And a more concrete connection between the concept of maternal smoking and the genetic markers can be clearly established. And that's what I aim to do going forward. That's one of my first steps. But that's all. Thank you so much for listening.
Thank you very much, Ruth. Really nice work. So there's a couple of questions that I think we have time for. So one, I think you answered a bit about what was your Python background when you started the project?
So when I first started the project, I had like it was very minimal. I had done some work when it comes to like basic Python and regular code, but then going forward after that, I sort of had to pick up on some of the specific libraries that I didn't really have access to. But before that, it wasn't very in-depth knowledge for me for Python.
Makes sense. And did you have any findings on the variance in a cross-validation? Did you have a chance to do any cross-validation?
Actually, that's another thing that I have to go back and look into. I really didn't get a chance to look at any of the cross-validation, but that's something I definitely need to add to my work going forward.
And then I think the final question was, can you tell us a little bit more about what was in the genomic information?
Great. Yeah, that's a good question, actually. So the genomic information itself, it consists of, the data set for this whole project, actually, it just came from a live sample for like 40 patients that were taken within a hospital in Russia. And so this is live information that they accessed through the lab and they had performed experiments on it for the team's own research as a separate project. But then coming here, this has some topics such as the genomic information specifically just has like the upregulated genes in terms of what when assessing a specific patient, what genes are showing higher values in terms of cord blood code 9 levels, and also for specific genes like there are a variety of names. I think there were close to 130 genes that were included, but the genomic information was just showing which were upregulated, which were downregulated, and giving like, expression values and like a correlation coefficient to show how much influence each gene had.
Got it. Thank you very much. Really nice work. And there's a lot of great comments for you on yeah. I think we'll probably hold off. I think there's one more question, but I think maybe we can take that one offline. So So thank you very much. I think we are now going to we're running just a little behind schedule, but only a few minutes. So we're going to take a 5-minute break. We will come back here 5 minutes from now at so for those in Pacific time, that would be 11:35 a.m. I'm going to stay on the call. You can stay on the call, and then we will have our next speaker, who let me just tell you ahead of time who it is so that you know. So our next speaker will be Savar Tuteja, and he will be speaking about how to use, I'm going to share my screen, how to leverage machine learning for understanding effective teaching strategies for children with autism spectrum disorder. So 5 minutes, and we will be back to hear from Savar. Thank you, everyone. See you soon.
都没有人。
Hi, we are on a break. We'll be back in like another minute or two, I think.
They were just on break. They were just on break. Okay.
Lunch. Hi, everyone. We're starting up again. So, just a second. So, is Savar here?
Yes,
Savar?
I'm here.
Okay,
Hello.
great. So, let's take it away, Savar. Go ahead and share your screen. You can start your presentation.
你要不要去跑一下？现在有 code again. Run up and down once.
Hold on. Go ahead, Savar.
All right, perfect. Can you see my screen?
Yes.
All right, perfect. Okay, so hello, everybody. I hope you're all having a great day. My name is Savar Tateja. I'm a student. I'm at Metuchen High School in New Jersey, and this is a project titled, oh, whoops, sorry. And this is a project titled Leveraging Machine Learning to Identify Effective Teaching Strategies for Children with Autism Spectrum Disorder. So if I had to describe this project in one long sentence, this study evaluates the use of machine learning algorithms to identify personalized teaching methods for children with ASD and develops a model for educators to implement more efficient and inclusive educational strategies tailored for individual students. Why this project? Children with autism encounter a range of educational challenges that can significantly impede their learning and development. These challenges include difficulties with communication, social interaction, and repetitive behaviors, which can affect their ability to engage with traditional teaching methods. Addressing these challenges requires specialized, individualized teaching strategies that cater to their individual needs and strengths. My personal motive for this project comes from my volunteer work, teaching children with special needs how to play sports. After seeing their circumstances and isolated education from others, I was inspired to do something to help. And I thought, what better way to do that than with machine learning? So like many students here, my solution was an AI model. An AI model offers significant advantages over traditional time-consuming and costly consultations with specialists. It quickly analyzes a child's needs through a simple 10-question questionnaire, providing immediate personalized recommendations crucial for early intervention in ASD. This cost-effective approach can be used repeatedly, making it accessible for more families. Additionally, AI-driven recommendations are consistent and objective, relying on data and patterns rather than subjective human evaluations. This ensures a standardized approach, leading to more reliable and effective educational outcomes. For software, Google Colab was utilized for the coding in this study. The programming language used was Python, and for sourcing the datasets, we utilized Kaggle and GitHub. In terms of datasets, 4 datasets were combined for this study: autistic spectrum disorder screening data for toddlers, behavior analysis of autism, and 2 versions of autism screening child. These were the datasets used. The survey focused on toddlers under 3 years of age, where parents answered 10 yes or no questions regarding their child's behavior, forming 10 features named A1 through A10. The remaining 7 features were collected from the ASD Tests screening app. Due to the insufficiency and general nature of individual datasets concerning clinical or screening autism spectrum disorder, all datasets were combined into a single uniform dataset. The final dataset contained 3,043 samples with 17 features. By leveraging machine learning algorithms, we were able to discern patterns and correlations in the data, which informed personalized educational plans tailored to the unique needs and strengths of each child. 4 different AI models were trained on the comprehensive dataset. These 4 were KNN, Decision Tree, Random Forest, and MLP, or Multi-Layer Perceptron. KNN was trained with K values ranging from 1 to 20 to find the optimal number of neighbors for classification. As shown in the left figure, the K nearest neighbors model's performance varied with different K values, peaking at 80.625% accuracy with K equals 9. The decision tree model was trained with max depth values ranging from 1 to 7 to optimize its performance. It peaked at a max depth of 7. Random forest was tuned with 2 hyperparameters, max depth 1 to 7 and the number of trees 10 to 100. The random forest model's performance peaked at a max depth of 7 and 50 trees. MLP performance was evaluated across various learning rates and training epochs. The highest accuracy, over 98%, was observed at learning rates of 0.01 and 0.05. In the end, here were our final results. In training, KNN achieved an accuracy rate of 80.62, decision tree 94.37, random forest 94.92, and MLP 99.29. In testing, KNN achieved 81.62, decision tree 96.88, random forest 95.01, and MLP 100%. While my biggest learning experience was that creating an AI was not as easy as it looked in movies, we had 3 more nuanced learnings. First, the importance of data quality. The success of machine learning models depended heavily on the quality, completeness, and relevance of the data. We learned that data pre-processing was essential for accurate and reliable outcomes. Second, adaptability. Our AI-driven approach demonstrated the potential for higher personalized educational strategies. By analyzing individual questionnaire responses, the models could tailor educational methods to each child's specific needs. Finally, model performance variability. Different machine learning models showed varying performance levels. The MLP model achieved perfect testing accuracy, while models like KNN and Decision Tree provided valuable insights, underscoring the importance of model selection and tuning for optimal results. Now, the challenges section could take about 4 days to get through, but here are the three biggest challenges we faced. First, gathering comprehensive data sets for ASD screening was difficult due to varying formats and quality. We solved this by sourcing data from Kaggle and GitHub and implementing rigorous pre-processing techniques. Second, selecting and tuning machine learning models required iterative testing. This was solved by extensively experimenting with MLP, decision trees, random forest, and KNN. Lastly, translating machine learning outputs into reviewable and easily understandable results was quite the difficulty. We addressed this by using visualization techniques such as confusion matrices and learning curves to clarify model performance and practical applications. In the future, we aim to expand our testing to include more algorithms, enhancing our ability to find optimal solutions. We're committed to continually improving and updating our datasets to ensure accuracy and relevance. Importantly, we plan to integrate feedback from educators, parents, and caregivers, ensuring our interventions adapt effectively to real-world conditions. Together, we're advancing towards more effective and personalized educational support for children with ASD. Thank you.
Thank you, Savar. Very nice presentation. So there's a couple of comments as well. So somebody felt that your project is very valuable, particularly in the education sector. There is one question about, can you talk a little bit about how you combine the data sets? Like, did you use Python, for example? How do you
For the combining the data sets, we utilized Google Colab. We plugged the data sets into Google Colab and then had to morph them and edit some columns out, and make them uniform, and then combine them into one big giant data set. So yeah.
Wonderful. Thank you very much, Savar. Great work.
Thank you.
Okay, so let me share my screen really quickly and introduce the next speaker. Hold on a second. Quite sure why I'm not sharing properly. Here we go. Okay. So next presentation is on brain tumor classification, and it will be presented by Mahum. Mahum, are you here? Like to share your screen?
Yeah, just 1 second.
Take your time.
All right. Can you see it?
Yes, you can see it.
Okay, perfect. Well, hi everyone. My name is Maham Jahangir, and I'm really grateful to be here today. Earlier this year, I worked on a project that kind of lives at the intersection between neuroscience and AI, and today I'm really excited to share a little bit about this project, which uses machine learning to perform brain tumor detection and classification. But before we get into the project itself, I thought it would be important to set some context and understand what a brain tumor actually is. So brain tumors are masses or growth of abnormal cells in the brain, and they can be either cancerous or non-cancerous. And there are lots of different types, but the three most common types and the ones that I focused on in this project were gliomas, meningiomas, and pituitary tumors. And then to detect and diagnose these tumors, doctors use lots of different scans, but the one that I worked with in this project was brain MRIs. Along with understanding brain tumors themselves, it's also crucial to understand why this is such a serious issue in our world. So these tumors have a huge impact on patients, as the survival rate of cancerous brain and central nervous system tumors is only 36%. And on top of that, diagnosis and treatment is also incredibly expensive, with overall treatment costing roughly $300,000, but it could be even more. And obviously, there's also this huge emotional impact on patients and their families. So clearly, this is a massive problem, and it's vital that we take action to alleviate this issue. So just in summary, the brain tumor diagnosis process requires a ton of time and money, which unfortunately many patients don't have. But this gives us an opportunity to explore some solutions. And this is where AI can be a game changer. So obviously, with the help of the presentations today, you all know what AI and machine learning is, and most likely you've used these tools in your daily lives. But what I've learned is that one of AI's most powerful strengths is accurate, efficient pattern recognition. So Face ID on your phone is a great example of this. Behind the scenes, an ML algorithm is taking note of features on your face, and it recognizes these patterns on your face to unlock your phone. And then we can take this exact pattern recognition and apply it to healthcare to improve the disease detection and diagnosis process. And after researching and learning more about this topic, that's exactly what I did. So to start off the process, I picked out a research paper to teach me more about brain tumors and ML and kind of guide me through the process. I worked on two separate ML models, one that simply detects if a brain tumor is present in the scan or not, and then another one that uses a different data set to actually classify the type of tumor that's present. And you can see these differences reflected in the data sets themselves. So data set 1 right here is much smaller, and it only does binary classification, but data set 2 is larger, it's more diverse, and it works with more than 2 classes. Next came actually building the models. So the data sets that came with the research paper I picked out, they already had clean pre-processed data, so I didn't have to deal with reformatting and things like that. For me, the first step was to split up the data into train and test sets. So just like how you learn and study material for a class before taking a test, that's exactly what the ML model is doing, and it has to learn patterns from training data and then test that learning on new data. After organizing my data, I wrote code to set up the model by linking my data to algorithms so that the model could successfully learn. And then I ran the models and ran experiments, or I trained the models and then ran experiments, tweaking different parameters to find the highest accuracy. And if you're curious about what that looked like, here's a quick look into some of my experimentation. My ultimate goal was to get the highest model accuracy possible. And so to do that, I had to change certain parameters and see how accuracy was impacted. So the two parameters I played around with were the number of epochs and the learning rate. So one epoch is essentially just one pass through the data set during training. And in very simple terms, learning rate is just, I guess, how quickly the model is learning new information and patterns. So since brain tumor detection and classification relies on images and scans, I used a specific kind of ML called convolutional neural networks, or CNNs. And this is just a tool that specializes in image analysis. So I guess a high-level description. First, you take an image and convert it to a numerical representation in the form of a matrix. And then each layer of the CNN is identifying a particular pattern. Some are identifying edges or textures or something else. But how exactly does the CNN read the matrix? Well, one way to think about it is if I give you a picture, but instead of letting you look at the whole thing, I only give you one little window that you can slide across the image. And every time you move the window, you learn something new about the image at a pixel level. And this is essentially what's happening behind the scenes. And at the end, the information from each layer gets converted into a prediction. And this sliding window allows the algorithm to make note of minor details in an image, which is something that humans can't do very well, which is why this is such a great solution. And then I explored 3 different types of algorithms as well, but MobileNet V2 proved to be the most efficient while maintaining this high accuracy. So now on to my results. So the first model, which focused on basic brain tumor detection, it achieved 100% accuracy. And although it's unusual for ML models to achieve perfect accuracy, especially so quickly, this result was possible due to the small data set and relatively straightforward classification task. I mean, it's pretty easy to tell if there's a tumor in a scan versus if there's not. There are also lots of metrics that we can use to figure out how well the model is performing. So one key way to do that is using a confusion matrix like this one on the right. Essentially, this is just a table that lays out predictions and actual values to help us see how often the model predicts an outcome correctly, and then to derive different performance metrics as well. Here are some accuracy loss plots and ROC curve of my first model. So loss measures the gap between predicted and true values. And we want this gap to decrease as shown on the left. So we can see that loss is dropping. But on the other hand, we aim to maximize accuracy. So that should rise. And then the ROC curve on the right shows the balance between false positive rate and true positive rate. And the closer the curve is to the upper left corner, the better the model performs. With my second model, which did classification of different types of brain tumors, I was able to reach 94.12% accuracy. And this time you can see the confusion matrix has grown to include all three classes, and it looks a little different than the matrix from the first model as it has slightly lower accuracy. And then the loss and accuracy plots have also slightly changed to reflect the 94% accuracy, but overall we still see the same general trends with loss dropping and then accuracy rising. So one of the biggest eye-openers for me throughout this project was the vast amount of opportunity there is for this technology in the healthcare field. As AI is growing stronger and more powerful, things like quick and reliable diagnoses will come in handy. And in terms of this project specifically, I have a few things planned that I really want to experiment with. So first off, it's really important to have diverse, well-rounded data. And so I want to try and find data with a wider variety. You saw my first data set, it was very, very small. And so I want to experiment with larger ones. And I also want to experiment with more machine learning algorithms and see if I can improve the model's accuracies even more. Accuracy is just such an important thing, especially in the healthcare field, because people's lives are on the line. And then on top of that, you don't want to misdiagnose someone. Okay, in terms of what I learned, so this project was my first exposure to applying AI and machine learning to another field like neuroscience. And through that, I was able to gain like a completely new perspective on the applications of AI. So a lot of the time, AI seems like this imaginary or like in my head, almost like magical thing because of how much power it holds and how like you see something happen right before your eyes and it's like you don't even know what's going on behind the scenes. But when you learn about AI at a deeper level and you start to understand like the mechanics of it, I think it changes your perspective a lot, and that's kind of what happened to me through this project. The project also helped me learn how to apply AI knowledge that I've gained, and something that stemmed from that was learning how CNNs work specifically and what they're designed for. And then finally, one of the biggest things that I learned was the importance of understanding AI's role in healthcare. So people are really quick to assume that we want to replace healthcare workers or doctors with AI, when that's actually not true at all. AI's role in healthcare is just to be a tool. And just like current machinery that's used in hospitals, they're all tools that we use to improve healthcare outcomes. And that's it.
Thank you very much. Lovely presentation.
Yeah.
So there's a few questions. So first of all, I think, everybody's very happy with your results. Can you talk a little bit about what role did you have with Python for your experiments? Did you use any GPUs along the way?
Yes, I actually had to. So when I was doing my experimentation, I experimented with different algorithms. I used MobileNet v2, ResNet, and I actually tried to use ConvNext, which is like a very complicated, very, I guess it's a very consuming algorithm. And so I had to use a ton of extra compute power to help me do the training. And eventually I had to stop halfway through because it was just taking too long, like the overall process. But yeah.
Perfect. And then there's a question about, is there a way to expand this project beyond tumor classification?
Absolutely, yes. So AI actually has a huge role in healthcare, not just like tumor classification. It can also read really any kind of medical data, and it can pick out, I guess, anomalies or abnormalities, and it can help with so many things. I've seen it being used with detecting strokes, at least in like the neuroscience fields, or I don't know, things like different abnormalities in your brain. And as long as you can convert the medical data to a way that you're able to put it through a neural network or machine learning, it's a great, way to do like detection and things like that.
Perfect. Thank you very much. Very nice work. And there's some nice, kudos for you on the chat that people are talking
Thank
about.
you.
Thank you, Mom. So I'm going to share my screen. So next up, we have Pranav. Pranav will be talking about assessing large language models for math tutoring effectiveness. So another education technology application. Wonderful. Pranav, are you here? Okay, I see you there. Yeah.
Yep.
All right. Go ahead and unmute. Yeah, and then you can share your screen.
Can you guys see my screen?
Yes, we can.
Perfect. Yep. So my project is called Large Language Models and Individualized Math Tutoring. And my name is Pranav Goyal, and I'm a rising senior at Hinsdale South High School near Chicago. So quick project description. So my project is about helping students with their math word problems without giving them the direct solution to their problem. It's a web interface coded in Python to help the students learn. And I've created 3 different pipelines and compared their performances as part of this research. So the problem motivation. In the past decade or so, especially after COVID-19, math performance, especially among middle school students, has been like declining significantly, between 6 to 15%. In addition to that, standardized test scores and like fundamental math knowledge has decreased. And to make matters worse, like your conventional 25 to 30 student or 25 30 to 1 student to teacher ratio has not been working to help like students learn at the level they need to continue with math. So my goal with this project was to help improve fundamental math knowledge in middle school students via a personalized AI tutor. So my solution. So I developed a user-friendly web application to tutor students in their math word problems. And the way this works is the student will input their question onto our web interface, and they will receive a similar question with its corresponding solution. So they won't get the answer to the question they asked, but they should get a similar question and a step-by-step breakdown on how to solve that similar question. Like the reasoning behind this was that it teaches the student a concept and how to like continue to solve it and understand it in the future instead of just getting like the solution to a one-time question. And then if one question is not enough, or if students want to like see more similar questions, they can pick anywhere between 1 to 5 questions. So a quick software interview. I used GitHub to find my data set that I used to train the models on. Most of the work was done on Google Colab, used for all the coding and training the models, and everything that was done with Python. And then actually to deploy the apps and get like a user-friendly, like very simple interaction with the students was done via Streamlit. So the data set. My data set was the GSM8K data set, which was picked from GitHub. It consisted of 8,500 stronger, like advanced middle school word problems. And we used 7,500 to train our models and 1,000 to test the questions, like to test the model. And within this data set, each question contained a step-by-step solution breakdown. So like it guide your thinking, and that's why we chose this data set. After finding this data set, we then downloaded it and converted it to numerical vectors. And we did this 3 times and embedded them with the 3 AI models we used. So I used 3 different large language model embeddings, each consisting of a varying and increasing amount of parameters. So the first model I used was BERT, which is your generically trained language model, and it has 110 million parameters. It's your normal language processing model, I guess you could say. Then we used a variation of BERT called MathBERT, which is similar to BERT, but it's also focused for math terminology, so it better understands your addition, your multiplication, your variables, your x, your y, and that had 383 million parameters. And then lastly, we used the OpenAI GPT 3.5, which at the time of this project was their largest and most sophisticated model with 175 billion parameters. So now for the actual process of how this works. The student would enter their question into one of the 3 AI embedded apps. Their question is converted to numerical vectors using one of the 3 embeddings. And then we used behind the scenes cosine similarity to measure the closest question to the one that the student entered in comparison to like the data set we had that we trained our model on. And then that question, or I guess 1 to 5 questions that the student wanted, was displayed with the solution so that the student could learn from it. So experiments. First off, my goal was to help the students better understand their math questions and like make sure they actually understand the concept instead of just getting a solution and kind of skipping through it like a lot of math tutors do currently. And then like this was a little bit more for myself as well, but I also wanted to see if like a different AI embedded model would provide better similar questions and therefore be more helpful to the students. So to test this experiment, each of the 3 web apps was sent out to middle schools in my neighboring counties. I had over like 100 middle school students type multiple questions that they were struggling with onto each of the 3 apps. And then after that, they'd like go through the solution in the similar question, and they would rate if that question was helpful or not, like based on how similar it was, and if like they learned something from it. And to like actually collect the results, I used a scale of 0 to 6, where 0 represents the question being shown was actively harmful to the student's learning, and 6 means that the question was extremely helpful to their learning. So my results. Across all the questions tested on all 3 of the models, OpenAI's GPT 3.5 proved to be the most helpful. And it's not that surprising considering the increased amount of parameters, and it was being the most sophisticated of the 3 models. And then to further verify that this was true, I used statistical tests. So I conducted a 2-sample t-test to ensure that there's a statistically significant difference between like the OpenAI and BERT and then the OpenAI and the MathBERT, which there was. But interestingly, the MathBERT and BERT model did not show statistical difference between them. So it could just be a little bit due to like error or like 1 or 2 questions being a little bit better, as you can see by the graphs on the screen. So learnings. First off, my biggest learning was probably Python. I had pretty basic knowledge beforehand. I was a little bit more proficient in Java, but I got like a lot more proficient in Python, like understanding how to use like the associated apps like Streamlit, GitHub, and then like also incorporating different libraries such as pandas. I also like learned how to properly like a research paper. So like using the tone, evidence, citations, language, restrictions that you want for publishing it. And then lastly, I also learned like how important it was to have like a good data processing and evaluation metric, because like without a good system and like statistical tests, getting a concrete like claim for which model was the best would have been pretty hard. And then lastly, if I had to improve some things for the future, I would like to increase the data set that our models are trained on, because currently my data set lacks like basic math, so like pretty like elementary addition, multiplication, subtraction. It wasn't trained for that. So like if a student enters that in like 5th grade, their question probably will get a little bit more harder than what they're looking for. And then on the opposite end of that spectrum, it also lacks like advanced math topics beyond like algebra 1 and geometry. So if I could train like the model to get those kind of questions in, it could be more helpful for a wider range of topics. And then these are like a little bit smaller, but if I could get into like a mobile app instead of just like on your web browser, that'd probably be a little bit more helpful, and maybe experimenting with like an offline mode. So here I'll show a quick demonstration of my app. So this is what my web app looks like. This is the OpenAI model. And I have a sample question, so we can test one of them right now. Tim can read 10 pages of a book in 30. How many can it take him to read 120? Okay, I copied this last question down, but so this is like the question. This is where the student would input their question. I'm just choosing one similar question right now, and then the model returns. So instead of 40 out of 100 like basketball and 30 play it, how many would you expect out of a group of 300? This is saying if 24 out of 60 like football, and out of those 50 play it, how many would you expect a group out of 250? So as you can tell, like this is this question a student could hypothetically enter. This is a similar question that our model gave them. And then following it is like a step-by-step breakdown with questions to guide like the students' thinking. So like first asking how many play football, and like so on and so forth. And like this makes sure that students like actually understand the topic. And then in the end, like a student would see this feedback bar on your left-hand side of the screen, and they could rate how helpful this question was to their learning. And yeah, thank you. I'll be happy to take any questions.
Thank you very much, Pranav. Great talk. So there are a few questions. There was a question on whether there's a link to the website that other people can try. Is there?
Yeah, I could send that right now.
Yeah, just plop it onto the Zoom chat. That way people can go ahead and try it and give you feedback.
This is the OpenAI, but I can also send the BERT and MathBERT model if you guys would like that as well afterwards.
I think yeah, you can how about you send it to the AIClub staff, and we will include it in the when we send out the link with the video.
Perfect. I can do that.
Everyone can have it then. And there's a comment that this is a great way to crowdsource assessment of of models. So it's great that you
Thank you.
gathered data. And then somebody asked you whether you used a vector database. Did you? I don't think you did, but can you comment?
No, yeah. I did not end up using any vector database for this project because it wasn't really necessary, I guess. It was just more converting our CSV files that we downloaded into like a numeric standpoint, and then we used cosine similarity because we found out that was the best way to test similarity for a question that a student answered in comparison to like the 8,500 questions that we used to train our model on.
Wonderful. Thank you very much, Pranav. Nice work.
Yep. Thank you.
So share my screen. So next presentation, just a second. Next presentation will be by Rohan Kaushikan. It will be about early recurrence detection of invasive ductal carcinoma using high dimensional genomic data. So go ahead, Rohan.
All right, cool. All right, can you all see my screen here?
Yes.
Okay, cool. All right, so my name's Rohan. I'm a high schooler in Menlo Atherton High School in the San Francisco Bay Area. And yeah, my project is machine learning directed at healthcare. It's called Early Recurrence Prediction for Invasive Ductal Carcinoma, utilizing high dimensional gene expression data. So let's actually kind of look at what invasive ductal carcinoma is. So I'll refer to it as IDC from now on, and it's the most common type of breast cancer. So actually over 80% of breast cancer cases are IDC. So that constitutes hundreds of thousands of IDC cases in the United States alone, and of course that number is so much bigger globally. So there are, multiple forms of treatment. There's like chemotherapy, radiotherapy, hormone therapy, as well as multiple surgeries for IDC. But even after that, there is a 3 to 15% chance that IDC can still recur after treatment. So my project was kind of aimed at forecasting that recurrence as early as possible, which would, help patient survival in the long run. So let's look at my hypothesis here. We thought we could use mRNA expression data to predict IDC recurrence at least one decade in advance, and predictably we were using machine learning to do so. So we thought that if we could diagnose recurrence of IDC as early as possible, we could inform treatment decisions in the healthcare field, and that would help patient outcomes. So to overview the software, the project was done on Google Colaboratory and was done completely using Python. Some specific libraries we used were Matplotlib. We want to visualize a lot of our data and represent them in like line plots, for example. So Matplotlib was used for that. We also used Pandas for data pre-processing. We had a pretty big data set. And we also wanted to process the data, filter out some data points. And then lastly, we used scikit-learn to import our two models that we used for prediction, random forest and XGBoost, and also to do the train test validation splits. So let's take a look at our actual data set here. So our data set was from the Cancer Genome Atlas, or TCGA, and it was on the breast invasive carcinoma study. So it included 1,084 patient samples, and 856 of those samples were not recurrent for IDC, whereas 84 were recurrent. And as you can probably see, that's a pretty big skew in our data set, which would affect our model results later. And then 144 of our data points were not categorized as being recurrent or not. So we did not use those at all. So here we have an image of what our data set kind of looked like. A little example. One important point of our data was that the genomic data was profiled about 11 years before IDC recurred. And that's like probably the most crucial part of my research here, because we do have currently methods of identifying recurrence before it happens, but most of these methods do not do so on such a large time frame of like over a decade in advance. So if we were to actually have promising results here, that would be a pretty great addition to the healthcare field. And the last thing was our data set was high dimensional. It included data, mRNA expression data for over 20,000 genes. So if we were to feed all of those data points into our model, that would be over 20,000 data points or features that our model has to incorporate into an algorithm, which we wanted to kind of address that, and we will soon. So the two models we chose to work with were XGBoost and Random Forest. And both of these work kind of similarly. They both use decision trees, whereas XGBoost trains decision trees sequentially, whereas Random Forest uses an ensemble. But they do have similar like hyperparameters, which we would fine tune. Now, they both also work quite well on data sets with a moderate number of features. So our data set did not have a moderate number of features, it had a very large number of features, but we want to kind of, trim that down. All right. So here I have a visual methodology. It's an overview of my methodology, and I'll go more into this in detail. But just to kind of give that overview, we had our initial data set and pre-processed that, and then we did a data split into training data, validation data for fine-tuning hyperparameters, and then finally testing data. So we initially trained our two models on the training data, fine-tuned hyperparameters using the validation set, and lastly, we tested both of our models to kind of gain our final results. So there were two things we did to trim down our number of features from over 20,000 to about 50. The first thing we used was mRNA differential analysis. And if you look at our data set, we have two kind of cohorts. We have patients for whom IDC recurred and patients for whom IDC did not recur. So one way of going about trimming down the number of features we used was looking at genes who are like most differently expressed between the two cohorts. For example, if a gene is very much expressed in recurrent patients but not in non-recurrent patients, we might want to use that gene, right? However, we kind of tested our model and realized our recall scores were quite low. Our accuracies were lower than we wanted them to be. So we opted to use principal component analysis. So what this does, PCA, it transforms our original data set into a new data set where each feature is not an mRNA expression value for just one gene, but it's a linear combination of mRNA expression values for all 20,000 genes. So now when we took our new data set, our PCA data set, and we trimmed that down to our top 50 features, we were actually able to retain over 90% of our original data. And we were also able to trim down the number of features to make it more workable for our model. So we fine-tuned hyperparameters. For both models, we used max depth, which are the complexity of the decision trees used, and the number of estimators, or the number of decision trees used for each model. And we have our ranges for each hyperparameter here. So here I'd like to go over the results on our validation set. So this is just our validation set, not our testing set yet. But as you can see, these line plots kind of show that our model accuracies were quite similar for both Random Forest on the top and XGBoost on the bottom, around like 92 to 94% accuracy. And through this, we were able to kind of pick out the most effective combination of hyperparameters. So now let's actually look at the confusion matrices, and these kind of represent the three metrics that we use to evaluate our models. So of course we used accuracy, the overall accuracy, but we also wanted to evaluate our model's recall score and precision score. So when we used all this, we noticed that our Random Forest model performed better than our XGBoost model on all three metrics, not by a super significant margin, but it was enough to kind of conclude that our Random Forest model was the best, with hyperparameters max depth 25 and number of estimators 500. So that is a model that we actually tested on our testing set. Okay, so to conclude, our metrics were an accuracy, if we go back here, of 95% with our best Random Forest model, a precision of 83%, and a recall of 56%. So let's break that down here. First of all, we can kind of see our model is pretty effective in a medical setting, not necessarily as the sole indicator of whether IDC will recur, but at least as a second opinion. So our recall score of 56% kind of suggests that over half of the recurrent cases, over half of patients who would have IDC recur, our model identified those using data collected over 10 years in advance. And normally, recall score of 56% is not too desirable, right? That's normally lower than we would want. But in a medical setting, if you think about it, where tens of thousands of patients will have IDC recur, identifying over half of those, over a decade in advance is still tens of thousands of lives that we could, improve if we use this model. And then secondly, our precision score suggests that if our model did call out a sample as recurrent, there's an 83% chance that it actually is recurrent. Okay, so to move on to the challenges, our first challenge and a major challenge was a lack of data. There were very few data sets, showing the kind of recurrence data we wanted here. And even once we settled on a data set, 1,084 samples, that number could be improved. And I kind of predict that if we were to increase the number of samples we have by finding more data, we could increase or maximize the performance of our model. Secondly, the low recall score. Which we initially encountered when we used differential analysis. We combated that by using principal component analysis, and that really greatly improved our recall score from like low 20% to 56% where it is now. So in the future, there are multiple ways we've kind of identified that we could improve our model's performance. So the first thing was to kind of create a multimodal model. So right now we're only using genomic data, but we could, improve that if we used image data as well. So the Cancer Genome Atlas has tissue slide images of patients with and without IDC. Or with and without IDC recurrence that we could use alongside our genomic data. So then we would be using both image data and genomic data, and that would kind of make our results more reliable and accurate. And secondly, if we used more genes as features, we could kind of make our data set more robust and hopefully maximize model performance from there. So that's all I have for now, and I'm happy to take questions. If we don't have time as well, I'm happy to respond to questions in like a direct chat as well.
Thank you very much, Rohan. I think we can have time for one question. There's a
Okay.
question about when you say high dimensional, like what's high dimensional?
So that kind of refers to the number of columns we had in our original data set. So we were working with genomic data for, I think it was around 20,600 genes, right? So if we were to use that data set, that's a high dimensional data set because it just has so many features that our model has to work with. And we address that by cutting down the number of features from over 20,000 to around 50. So yeah, we were originally working with a high dimensional data set and we addressed that.
Wonderful. Thank you so much, Rohan.
Yeah, no problem.
Okay, so next up, we have an entirely different area. So Aditi will be speaking about a neural network approach using deep learning for the image classification of polar ring galaxies. So Aditi, are you here? Perfect. Yeah, go ahead and share your screen and you can get started.
Okay. Is my screen visible?
Yes, we can see it.
Okay. My project is on a neural network approach using deep learning for image classification of polar ring galaxies, and I'm a rising junior in Wisconsin. The solar system has sun, planets, and orbits, and this solar system is part of a small galaxy, ours being the Milky Way. As we look into the night sky, we marvel countless galaxies, each telling a unique story. There are over 100 billion galaxies in the universe, and along with this, there are also many types. Spiral galaxies, elliptical galaxies, irregular galaxies, and lenticular galaxies. Polar ring galaxies are a type of lenticular galaxy. The reason for my study is that polar ring galaxies are rare with unclear origins, though many theories have been proposed. Studying these will help astronomers with dark matter research and understand the evolution of the universe. Manually classifying these polar ring galaxies has some challenges due to their unique structure and varied morphology and tendencies to look different from different angles. As our understanding of these galaxies evolves, so does the need to update our classification criteria, and artificial intelligence is a solution for this. AI utilizes 3D modeling techniques to overcome distorted projected images. This way, a larger polar ring galaxy catalog can be created, making an impact on future research. This is my study design. First, I obtained a non-polar ring galaxy and a polar ring galaxy. I split this data into 10% training, 10% testing, and 10% validation. I then created and trained a convolutional neural network, and after determining the best model, I tested it on a real unclassified dataset to see how it would perform in the real world. My polar ring galaxy dataset was obtained from the Sloan Polar Ring Catalog, which contains the polar ring galaxies from the Sloan Digital Sky Survey. I took the non-polar ring galaxy dataset from the Galaxy 10 SDSS dataset. This is separated into 10 class, which were then grouped into 2 categories, being disk and smooth galaxies. So the next step in my project was to train the neural network. A neural network is a method in AI that teaches computers to process data that is similar to the human brain. I used a convolutional neural network, which specializes in processing grid data. It has an input layer that takes in pixel values, a convolutional layer that applies filters, and then a max pooling layer, which stores the max values from the previous layers, and then a fully connected layer that connects every input neuron to every output neuron. Along with this, I also had to find the right combination of learning rate, batch size, and epochs, and these are called hyperparameters, and tuning these takes hundreds of experiments. I then had to use some pre-trained neural networks. ResNet 50 is a medium-sized network, and this consists of 50 layers. Residual blocks are the building blocks of ResNets. MobileNet V2 does the opposite of what residual blocks do. It contains inverted residuals connecting the narrow layers with skip connection and wide layers in between, but ResNet does not do this. VGG16, on the other hand, is a huge network consisting of 138 million parameters, making it one of the most extensive networks. So I had a wide variety of pre-trained networks, one being small, one being medium, and one being large. For training the models, I used all 3 networks. The training dataset had 80% of the data, the testing dataset had 10%, and the validation dataset had 10%. These models were created using the Python coding language. In my first model, I split the data into categories based on their colored bands. We tried to train the model using each image's color to correspond to the galaxy's morphology. But when we did this, the I, Z, and Y bands were undetectable, and this made the model classify the galaxies as only red or blue bands. The red bands are elliptical and lenticular galaxies, and the blue bands correspond to elliptical and barred spiral galaxies. Polar ring galaxies are a type of lenticular galaxy, so they had red peaks. A lot of other galaxies also have this red peak, which is what led to the misclassifications. In Model 2, I split the data into polar ring and non-polar ring categories instead. The coordinates from each galaxy had to be turned into images. So for this, an image extraction service had to be used. When we use the one from PanStars, you can see that the resolution is really low, and when we use SDSS, the resolution was very high. And this difference in resolution led to the model classifying based on the resolution rather than the actual galaxy itself. Models 1 and 2 failed, so in Model 3, we split the non-polar ring galaxy category into smooth and disk galaxies, because these are the ones that tend to get confused the most with polar ring galaxies. Grouping the 3 separate types of smooth galaxies into one class and the 7 different types of disk galaxies into another class helped get a more detailed classification. Here are the results of Model 3 and the confusion matrices that summarize the performance. ResNet 50 achieved the best accuracy, with an accuracy of 89.64%. As for the learning rates and epochs, I tested the learning rates from 10 to the negative 6 to 0.05. I tested the epochs from 10 to 50 epochs. I conducted 35 experiments for every neural network, and in total, I conducted 315 experiments. I had to apply Model 3 to the new general catalog, which is a real dataset that has 7,840 galaxies in it. The reason this is called a real dataset is because it has small amounts of each galaxy, unlike the training datasets. Our model extracted 426 smooth galaxies, 412 disk galaxies, and 4 polar ring galaxies at a rate of 130 galaxies per minute. To make sure that all of the galaxies don't get sorted into one category, even if it has a small resemblance, I established a cutoff of 90% confidence. Our model's most common misclassifications were merger galaxies instead of polar ring galaxies, because they both have 2 components to them. But these misclassifications are easier to sort through than picking out the polar ring galaxies from a huge dataset. My study complemented AI with manual verification, giving it the advantages of both. My study has an accuracy of around 90%. AI was not used to classify polar ring galaxies in the past, which is why these other studies are not a direct comparison, as they classify different kinds of galaxies. The limitation of my project would be the very small quantity of polar ring galaxies, and this could create imbalance. Creating augmented data or simulated data could be challenging, but this could be a future solution. In the future, our model could be tested on unclassified datasets of galaxies to extract more of them. One of these sky surveys is the Wallaby Sky Survey, which will have polar ring candidates in the future. Dark matter is one of the properties that polar ring galaxies have. The catalog of polar ring galaxies could be explored by conducting experiments on their rings, and galaxy evolution could be discovered. If there are any questions, I would be happy to answer them now.
Thank you, Aditi. Very nice work. So let me see if there are any questions. Sorry. So yes. So the question was, where did you find the data? Was it usable as it was, or did you have to do anything to make it usable?
Yeah, that's a great question. So the data set, I found it, it was actually at like the bottom of a research paper, so it took a little bit of digging to find it. But this data set, it was actually in the form of coordinates. So we had to get that into image format. So we used a couple different image extraction services, and that's kind of what we did in Model 2. So yeah, we had to do a little bit of experimentation to find the best type of resolution for that.
Makes sense. So you learned a lot about kind of how astronomical data like naturally presents, right? It's not as easy. Very nice work. Thank you, Aditi. Okay, just share my screen real quick. And last but definitely not least, speaker is going to be Harini. She's going to be speaking about wound image classification using DE GANs. Harini, want to take it away?
Yeah, thank you so much. Let me first share my screen. Okay, awesome. Can everyone see this?
Yes, we're good.
All right. Hi, everyone. My name's Harini Narayanan. I'm a high school student here in the Bay Area, and today I'm going to talk to you about my project on using data augmentation to realize the potential of AI in wound care. So let's first introduce our problem. Wound care is less accessible and way too expensive. The cost of individual patient care alone for pressure ulcers is around $20,000 minimum per year. And there are additional costs for the care of the wound that amount to around $43,000 per year. Now, AI has a huge potential to make wound care more accessible and more cost-effective. But in order to actually reach this potential, we have to overcome some key challenges around data and privacy, namely data scarcity. Oh, 1 second. Sorry. So why does data scarcity exist? We can't use real patient data due to privacy laws such as HIPAA that rightfully protect sensitive patient medical information. And we also want to find a solution that preserves patient privacy because patient privacy enhances treatment quality, prevents stigma, embarrassment, and discrimination. And this is only the tip of the iceberg of all of the reasons why we need to find patient privacy preserving solutions. So now let's talk about some past work. Some solutions have attempted to obtain data from patients with their consent. This takes a very, very long time to implement, and it often results in very small and unbalanced data sets, almost unusable. And other solutions have tried to, make do with what they have. They've tried to create classification models with very small and unbalanced data sets, but we end up seeing overfitting of the model, which is basically the model memorizing the data set. So this is a basic framework of my solution. I started off with a unbalanced wound images data set, and I did selective sampling, and I had a balanced but very small data set. With that balanced and very small data set, I implemented a base transfer learning model that can take in a wound and classify it between its different types. Due to my very small data set, I had to explore augmentation techniques. And so I first implemented basic augmentation with transformations, and then I implemented DE-GAN augmentation, which I'll go into in a sec. So going a little deeper into this, I used selective sampling to choose about 75 images for each category of ulcers or wounds. And now, in order to choose my very first transfer learning model, I tested a lot of different sizes of models to see which ones would work best for my solution. So I used MobileNet v2, ResNet 50, and VGG16, and I used many hyperparameter combinations to see which ones would work the best. After I found my basic transfer learning model, I implemented basic data augmentation through geometric transformations, and then I did GAN-based generative modeling to inflate my data set. So transfer learning, it essentially leverages the knowledge learned by foundational models trained on larger data sets, much larger data sets, and similar tasks, so that these models can then be easily specialized for a specific task. They have tons and tons of advantages, mainly one being speeding up the process of creating a new specialized model. It reduces the implementation time and reduces the amount of data needed, which is perfect because I didn't have much data to start with. And I used, again, the foundational models ResNet 50, MobileNet v2, and VGG16, and ResNet 50 ended up giving me the best results. Though these models are amazing in what they can do, they still suffer from data scarcity when they're adapted to new tasks through transfer learning. This is where data augmentation comes in. The basic data augmentation I used first was geometric transformations. There are many examples of this, such as flip, rotate, zoom, and brightness. I used rotating by a degree from 0 to 30, and I changed the zoom from 0 to 2, 0 to 0.2. And these have a lot of advantages as well, including combating overfitting, which is memorizing the model memorizing the data set. And they create different variations of the training images, which actually forces the model to learn patterns rather than memorize. Next, I used GAN-based generative modeling. Now, GANs are extremely complex, with each of the submodels, a generator and discriminator, having many, many layers of neural networks. But the basic idea is that a generator creates an image and a discriminator tries to tell them apart, and they have a zero-sum game and an adversarial nature that allows the final images to be produced to be very high quality. Now let's go over some of my results. Though my initial ResNet 50 model classified wounds with a pretty high accuracy of about 84%, it has a very low accuracy for class D, or diabetic ulcers, and class P, pressure ulcers. Actually, through the confusion matrices, I can see evidence of the model confusing between diabetic and pressure ulcers. So once I implemented basic augmentation, I saw an improvement in all the classes, and I used GANs to augment diabetic ulcers and inflate my data set. And I saw a decrease in the false positive rate for diabetic ulcers and an increase in the correctly classified images from 10 to 12. So this is just a side-by-side comparison. I have a wound image generated by a DE-GAN, which is a GAN, except it has more informed noise passed into it in the beginning, which allows the high-quality images to be created faster and with just better quality than a naive GAN. And this is my original or real wound image. You can see that there's a similar style, except it introduces variety and variation, which is what we need when we're inflating a data set. So the discussion. So overall, DE GANs were really, really good, and they increased our accuracy. But we had two difficulties along the way. The first difficulty was that DE GANs had a huge amount of sensitivity to changes in the patterns and images they were trained to generate. For example, a few of the images that they were trained with could have had a wound on your arm, and then one would randomly have a wound on a toe, and it would throw it off. So this finding actually led us to focus on only diabetic ulcers for this project. And even with Class D augmentation, it took an extensive hyperparameter search to find the correct DE GAN that would actually produce viable images. And this could be, again, because of our training data had a lot of variation. And once we found the correct model, we observed that the DE GAN would create a lot of very similar or almost the same images. Now, if you would ask why this happened, this is probably because of mode collapse. Now, mode collapse is when the generator finds one image that continually fools the discriminator, and so just keep on repeatedly producing that one image. Now, the conclusion. So basic data augmentation and GAN-based data augmentation proved to be very viable ways to enrich and grow training data sets and improve training accuracy. In terms of future work, I can first start off by implementing GANs for all the other classes than just the diabetic ulcers. And I can also experiment with other types of GANs, such as the Wasserstein GAN, which can help prevent mode collapse, which we talked about in the last slide. Overall, this study took the first steps in removing a huge roadblock to many implementations of AI in all fields of medicine. So, thank you. I'm happy to answer any questions you guys have.
Thank you very much, Harini. Great talk. So I think there was a question, I think you sort of answered it. It was a question of whether it was easy to generate these images. And I think the answer to that is no, but would you like to elaborate?
It's actually really funny that you asked this, because it is every single time I've ever described my experiences with GANs, I've always added the phrase "a labor of love" because they really were. There was a lot of times of uncertainty. I was wondering whether I would even get the GAN that would give me any images. And I definitely faced some difficulty with the GANs just because of again, the variation that I had and just the very unique task that I applied it to. But at the end, the images that I got, I think that it was totally worth it.
Wonderful. Thank you very much, Harini. Great talk. So I'm going to share my screen really briefly and just provide a few closing thoughts. So hopefully, for the attendees, hopefully you all got a kind of a sense of some of the points that were made fairly early on by the keynote speakers in particular, which is the sheer potential of AI and also the sheer potential for young people to really learn AI and do meaningful real world solutions very early and then prepare them for essentially a lifetime of using AI in pretty much every job that there is. Now, a few additional comments on why research before college, not just AI, but research in general. Research is fundamentally a problem-solving methodology. And learning how to solve problems is really useful because that is pretty much what every job in the world is about. The job may be specific, but at the end of the day, whoever's hiring you is hiring you so that you can solve a problem so that they don't have to solve the problem. And one thing that I generally advise students is that when you become more senior as adults, really fundamentally what it means is that the problem you're solving just got larger and less well-defined. And so learning how to solve problems, breaking it down, understanding what you know, what you don't know, what is your hypothesis. Behind every problem is a hypothesis, but research makes that explicit. So it's really a good thing. It also provides distinctive, achievements as well as ways to develop passions and areas of interest. And as you saw from the students, there are very many different areas that one can pursue. How do you get started? Find a topic that you care about, learn the research process. AI is really a very good thing these days for almost any kind of research because as Rob Ober mentioned, it's fundamentally a pattern matcher. And it can really help you learn things that are true, and it can also help you explore things that may be true. And then experiment and see what you learn. You know, for high school students, there are many goals and targets. There are science fairs, innovation competitions, publications, nonprofits or startups. There are many different angles that you can take to creating an outcome for your research project. Where does this typically fit into APs and the school curriculums? What you will find is that a lot of these kinds of things can be somewhat complementary, particularly in AP area. AI is not still integrated into the AP process. There are some very, very early discussions in the College Board about bringing an AP for AI, but it's not going to be for many years before anything like that is going to happen. However, we find that students who develop research skills, for example, get a really good solid head start on AP statistics, because many of the techniques that are used in research projects are the ones that you will learn in AP statistics, things like that. And there are some overlaps with other APs as well. The Research Institute, if you're interested in checking it out, it's actually, I think you can just send an email. It is also on our website as the Research Institute. And this will be included, I'm sure, in the video that is sent, the email that is sent out with the video. You can get a sense of what other students have done, some of the things they've won, some of the papers that they have published. These are all different papers published by our students. And that'll give you kind of a sense of what is possible, how to get started, and see if it's something that's of interest to you. And I think that is all that I had. Thank you very much for all the students and all the speakers. Wonderful job, everybody. And thank you so much for the students. I'm very, very proud of all the work that the students have done. And if you have any questions, please reach out, and you will be receiving information once the recordings are posted. Thank you very much, everybody, and have a great day. Bye-bye.